When we look up at the night sky, our eyes are naturally drawn to the gentle glow of celestial companions that dance around their parent worlds. These are the moons, silent guardians that have watched over planets for billions of years, each one carrying secrets that challenge our understanding of the cosmos itself. Tonight, we embark on a journey through space and time, exploring the most enigmatic moons our universe has to offer. From the familiar face of Earth's own lunar companion to the alien landscapes of distant worlds, we will discover oceans hidden beneath sheets of ice, volcanoes that paint the darkness with their fiery displays, and atmospheric puzzles that continue to baffle scientists around the globe. Our story begins close to home, with the moon that has guided human civilization for millennia, then ventures outward through our solar system to worlds so strange they seem born from the imagination of cosmic poets. We will visit places where geysers shoot ice crystals hundreds of miles into space, where methane rains fall upon alien shores, and where magnetic fields create invisible shields around worlds of ice and rock. Each moon we encounter tells a unique story of formation, evolution, and the delicate dance of gravitational forces that shape entire solar systems. Some moons are ancient, bearing the scars of cosmic bombardments that occurred when our solar system was young. Others remain geologically active today, their surfaces constantly renewed by forces we are only beginning to understand. As we travel from world to world, we will uncover how these celestial bodies influence not just their parent planets, but potentially the very possibility of life itself. The gravitational pull of moons creates tides that may have helped early life emerge from primordial seas. The protection they provide from asteroid impacts has shielded developing worlds from cosmic catastrophe. And in some cases, the moons themselves may harbor the ingredients necessary for life to flourish in the most unexpected places. The moon that hangs in our earthly sky has been humanity's first glimpse into the cosmic beyond for as long as our species has possessed the capacity for wonder. Every civilization that has ever gazed upward has woven stories around this silvery disk that waxes and wanes with mathematical precision. The ancient Greeks saw the face of Selene, goddess of the moon, riding her chariot across the heavens. The Chinese spoke of Chang, the moon goddess who lived in a palace with only a jade rabbit for company. Norse mythology told of Mani, who drove the moon across the sky while being chased by a wolf that would one day devour him during Ragnarok. But beyond the realm of myth and legend, Earth's moon presents us with genuine mysteries that continue to puzzle scientists today. At approximately 1/4 the diameter of Earth, our moon is unusually large compared to its parent planet. Most moons in our solar system are tiny compared to the worlds they orbit, yet Luna, as astronomers sometimes call her, maintains a size ratio that is virtually unique in our cosmic neighborhood. The leading theory for the moon's formation reads like a tale of cosmic violence. 4.5 billion years ago, when Earth was still a molten world covered in seas of magma, a Mars-sized object called Theia struck our planet in a collision so massive that it melted both worlds. The impact ejected enormous amounts of material into orbit around Earth, material that eventually coalesced to form the moon we see today. This giant impact hypothesis explains many of the moon's characteristics, including why lunar rocks brought back by Apollo astronauts show chemical signatures similar to Earth's mantle. Yet questions remain. Computer simulations of this ancient collision struggle to explain certain aspects of the moon's composition and orbit. Some scientists propose that multiple smaller impacts, rather than one giant collision, created our lunar companion. Others suggest that Earth and the Moon formed together as a double planet system from the very beginning. The truth may lie somewhere between these theories, or it may be something we have not yet imagined. The moon's surface tells a story written in craters, mountain ranges, and vast plains of hardened lava called maria. These dark patches, which early astronomers mistook for seas, are actually the remnants of massive volcanic eruptions that occurred billions of years ago. The largest of these, Oceanus Procellarum, stretches across nearly 4 million square kilometers, larger than the entire continent of Europe. One of the most intriguing features of our moon is its far side, forever hidden from Earth's view due to a phenomenon called tidal locking. Until the Soviet Luna 3 spacecraft first photographed the moon's far side in 1959, humans had never seen this mysterious hemisphere. What they discovered was a landscape dramatically different from the near side we know so well. The far side is heavily cratered and mountainous, with very few of the dark maria that characterize the side facing Earth. This dichotomy between the moon's two hemispheres presents another puzzle. Why should one side be so different from the other? Some scientists propose that Earth's gravity influenced the moon's internal structure as it cooled, causing the heavier elements to concentrate on the side facing our planet. This would have made volcanic activity more common on the near side, creating the smooth maria we observe today. Other theories suggest that a second moon once orbited Earth alongside our current lunar companion, eventually colliding with the far side and creating the heavily cratered terrain we see there. The moon's interior holds secrets of its own. Unlike Earth, which maintains a strong magnetic field generated by its molten core, the moon has only the faintest whisper of magnetism today. However, analysis of lunar rocks reveals that billions of years ago the moon possessed a much stronger magnetic field, suggesting that its core was once molten and dynamic. What caused this ancient dynamo to shut down remains unclear, though it likely relates to the moon's small size and relatively rapid cooling. Seismic monitoring stations left by Apollo astronauts detected moonquakes that occur with surprising regularity, often triggered by Earth's gravitational pull when our planet is closest to the moon. These quakes can last for hours, much longer than earthquakes, because the moon's dry, rigid structure allows seismic waves to propagate much more efficiently than they do through Earth's water-saturated rocks. Water on the moon was once thought to be non-existent, but recent discoveries have revolutionized our understanding of lunar resources. Deep craters at the moon's poles, where sunlight never reaches, contain billions of tons of water ice. This ice may have been delivered by comets over millions of years, accumulating in these permanently shadowed regions where temperatures drop to -230 degrees Celsius. The presence of water ice has profound implications for future human exploration, as it could provide both drinking water and fuel for spacecraft. The moon's gravitational influence on Earth extends far beyond the familiar ebb and flow of ocean tides. Our lunar companion acts as a cosmic stabilizer, preventing Earth's rotational axis from wandering chaotically over time. Without the moon's steady gravitational pull, Earth's axis could tilt anywhere from 0 to 85 degrees, creating wild climate swings that would make the development of complex life extremely difficult. Mars, which lacks a large stabilizing moon, shows evidence of exactly this kind of axial wandering in its geological record. The moon is also gradually moving away from Earth at a rate of about 4 centimeters per year. This recession is caused by tidal forces that transfer angular momentum from Earth's rotation to the moon's orbit. Billions of years ago, the moon was much closer to Earth, appearing enormous in the sky and creating tides hundreds of times stronger than those we experience today. In the far future, the moon will be so distant that total solar eclipses will become impossible, as the moon will no longer be large enough in the sky to completely cover the sun. Ancient coral fossils provide evidence of this changing relationship between Earth and Moon. By counting growth bands in coral that lived hundreds of millions of years ago, scientists can determine that Earth's day was much shorter in the past, and the Moon was correspondingly closer. 400 million years ago, a day on Earth lasted only 22 hours, and the Moon completed its orbit in just 20 days rather than the current 29.5. As we contemplate these mysteries of our nearest celestial neighbor, we begin to appreciate how much we still have to learn about even familiar objects in our cosmic environment. The Moon, which has watched over Earth for billions of years, continues to surprise us with new discoveries and unsolved puzzles. Its influence on our planet's evolution, climate, and possibly the emergence of life itself makes it far more than just a beautiful object in our night sky. But Earth's moon is just one member of a vast family of natural satellites that populate our solar system. As we prepare to venture outward from our homeworld, we enter a realm where moons become even stranger and more varied than we might ever have imagined. Some harbor hidden oceans that may teem with life. Others spew ice and organic compounds into space through towering geysers. Still others possess atmospheres thicker than Earth's own, complete with weather systems and seasonal changes that rival those of planets. Our journey now takes us beyond the orbit of Mars, past the asteroid belt, and into the realm of the giant planets where some of the most fascinating moons in our solar system await our exploration. Here, in the cold reaches of the outer solar system, we will discover worlds that challenge every assumption we might have about what makes a place suitable for life, and we will encounter landscapes so alien that they stretch the boundaries of imagination itself. The first stop on our outward journey brings us to Jupiter, the king of planets, whose retinue of moons reads like a catalogue of cosmic wonders. Among Jupiter's many satellites, Europa stands out as one of the most intriguing worlds in our entire solar system. From a distance, Europa appears as a smooth, pale sphere, its surface crossed by dark, linear features that create patterns reminiscent of cracks in Arctic sea ice. This resemblance is far from coincidental, for beneath Europa's frozen surface lies an ocean that may contain more than twice as much water as all of Earth's oceans combined. Europa's surface is composed almost entirely of water ice, but this is no ordinary frozen wasteland. The ice shell that encases the Moon is estimated to be 15 to 25 kilometers thick, floating atop a liquid ocean that may extend down 100 kilometers or more. This hidden sea has remained liquid for billions of years, kept warm by the same tidal forces that cause the Moon's surface to flex and crack as it orbits Jupiter. The complex pattern of ridges, bands, and chaos terrain that covers Europa's surface tells a story of constant geological activity driven by Jupiter's immense gravitational pull. As Europa follows its slightly elliptical orbit, the tidal forces stretching the Moon grow stronger and weaker in a regular cycle. This flexing generates heat through friction, not only keeping the subsurface ocean liquid, but also driving the formation of new surface features. Linear features called lineae stretch for thousands of kilometers across Europa's surface, often running remarkably straight despite crossing varied terrain. These features appear to be places where the ice shell has cracked, allowing material from below to well up and create new surface formations. Some scientists believe these cracks may occasionally breach the ice shell entirely, creating temporary connections between the hidden ocean and the vacuum of space. Perhaps even more intriguing are the regions of chaos terrain, where the normal pattern of ridges and lineae gives way to jumbled blocks of ice that appear to have been broken apart, rotated, and refrozen in new positions. These chaotic regions suggest that the ice shell has been locally disrupted, possibly by upwelling of warmer ice or even liquid water from below. The fact that these regions show relatively few impact craters indicates that they are geologically young, formed within the last few million years. The chemistry of Europa's ocean presents tantalizing possibilities for life. Water alone is not sufficient for biology, but Europa's ocean likely contains dissolved salts and minerals leached from the rocky core below. The interaction between water and rock at the ocean floor could create hydrothermal environments similar to those around Earth's deep-sea volcanic vents, where life thrives in the absence of sunlight. Europa's ocean may also contain oxygen, though not from photosynthesis as we know it on Earth. Jupiter's powerful magnetic field accelerates charged particles to enormous speeds, creating radiation that bombards Europa's surface ice. This radiation breaks apart water molecules, freeing oxygen that could potentially dissolve into the ocean below. While the surface radiation environment is lethal to life as we know it, the ocean beneath the ice would be shielded from this harsh radiation while still benefiting from the oxygen production occurring above. Recent observations have detected what appear to be water vapor plumes erupting from Europa's south polar region. These plumes, if confirmed, would provide a direct window into the composition of the subsurface ocean without requiring a mission to drill through the ice shell. Spectroscopic analysis of these plumes could reveal the presence of organic compounds, dissolved minerals, and other chemicals that would tell us about the ocean's potential for harboring life. The temperature of Europa's ocean likely hovers around the freezing point of seawater, cold by Earth standards but well within the range that life can tolerate. On Earth, organisms thrive in permanently cold environments, from Antarctic lakes to the deep ocean where temperatures remain just above freezing year-round. The stable, liquid environment beneath Europa's ice could have provided a constant habitat for billions of years, plenty of time for life to emerge and evolve. Future missions to Europa face the challenge of confirming what lies beneath the ice and determining whether the conditions there could support life. Several spacecraft concepts have been proposed, ranging from orbiting probes that would study the Moon from a distance to sophisticated landers that would analyze the surface composition and search for signs of subsurface activity. The most ambitious proposals involve ice-penetrating probes that would melt through the frozen shell to directly explore the hidden ocean below. The radiation environment around Jupiter poses significant challenges for any spacecraft attempting to study Europa in detail. Jupiter's magnetic field traps high-energy particles, creating radiation belts that would quickly damage unprotected electronics. Future Europa missions must be carefully shielded and designed to operate in this harsh environment, gathering their data quickly before radiation exposure becomes critical. Despite these challenges, Europa represents one of the most promising places to search for life beyond Earth. The combination of liquid water, chemical energy sources, and protection from the harsh space environment creates conditions that could theoretically support an entire ecosystem. Whether such life actually exists remains unknown, but the possibility continues to drive scientific interest in this frozen world that hides one of the solar system's greatest secrets. As we contemplate Europa's hidden ocean, we begin to understand that the traditional concept of habitable zones around stars may be too narrow. Europa receives very little sunlight compared to Earth, yet its ocean remains liquid thanks to tidal heating. This realization has expanded our thinking about where life might exist, not just in our own solar system, but around other stars as well. Our journey through Jupiter's system of moons continues to Io, a world that could hardly be more different from its neighbor Europa. Where Europa presents a serene face of smooth ice marked by elegant linear patterns, Io blazes with the fires of active volcanism, making it the most geologically active body in the solar system. Io's surface is painted in brilliant yellows, oranges, and reds, colors created by sulfur and sulfur compounds ejected from hundreds of active volcanoes. This small moon, only slightly larger than Earth's own moon, experiences volcanic eruptions so frequent and violent that they completely resurface the entire world every million years or so. No impact craters mar Io's surface because volcanic activity erases them almost as quickly as they form. The source of Io's incredible volcanic activity is the same tidal heating that keeps Europa's ocean liquid, but in Io's case the effects are far more dramatic. Io orbits Jupiter in a resonance with Europa and Ganymede, meaning that these moons return to the same relative positions on a regular schedule. This gravitational dance keeps Io's orbit slightly elliptical, causing the tidal forces acting on the moon to vary rhythmically. The constant flexing and stretching of Io's interior generates enormous amounts of heat through friction. This heat melts rock deep within the moon, creating magma that seeks escape through volcanic vents. The result is a world where volcanic plumes regularly shoot hundreds of kilometers above the surface, creating umbrella-shaped clouds of gas and particles that can be seen from space. Io's volcanoes come in several varieties, each producing different types of eruptions and surface features. Some are explosive volcanoes that launch material high above the surface in dramatic plumes. Others are effusive volcanoes that pour lava across the landscape, creating vast flows that can extend for hundreds of kilometers. Still others are volcanic hotspots where temperatures reach over 2,000 degrees Celsius, hot enough to melt silicate rock and create lava lakes that glow brightly in infrared observations. The composition of Io's volcanic emissions provides clues about the moon's interior structure. Most of the volcanic gas consists of sulfur dioxide, along with sulfur vapor and other sulfur compounds. However, the hottest volcanic regions appear to erupt silicate lavas similar to those found on Earth, suggesting that Io's interior contains molten rock beneath a sulfur-rich outer layer. Io's thin atmosphere consists primarily of sulfur dioxide gas produced by volcanic outgassing. This atmosphere is constantly being replenished by volcanic activity and constantly being lost to space, creating a dynamic equilibrium that maintains a tenuous gaseous envelope around the moon. The density of this atmosphere varies dramatically depending on volcanic activity levels and the heating effects of sunlight. Jupiter's powerful magnetic field interacts with Io's volcanic emissions in spectacular ways. Charged particles from Io's volcanoes become trapped in Jupiter's magnetosphere, creating a donut-shaped cloud of plasma called the Io plasma torus. This torus glows brightly at certain wavelengths and influences the behavior of Jupiter's entire magnetic field system. The interaction between Io and Jupiter's magnetic field also generates powerful electrical currents that flow between the Moon and the planet. These currents, carrying millions of amperes of electrical power, heat both Io's thin atmosphere and Jupiter's upper atmosphere, contributing to the complex electromagnetic environment of the Jovian system. Observing Io's volcanic activity provides insights into processes that may have been common throughout the early solar system. The intense volcanic activity we see on Io today may be similar to what occurred on Earth and other terrestrial planets during their formation, when radioactive decay and impact heating kept planetary interiors molten and drove massive volcanic eruptions. The study of Io's volcanoes also helps scientists understand how tidal heating works in planetary systems. By monitoring the locations and intensities of volcanic eruptions over time, researchers can map the internal structure of the Moon and test theoretical models of tidal flexing. These studies have implications not only for understanding other moons in our solar system, but also for predicting the geological activity of exoplanets orbiting close to their parent stars. Despite its hellish appearance, Io plays an important role in the Jupiter system's overall dynamics. The Moon acts as a source of material for Jupiter's radiation belts and contributes to the complex interactions between Jupiter's many satellites. Io's volcanic emissions also provide a natural laboratory for studying high-temperature chemistry and physics under conditions that cannot be replicated on Earth. From our exploration of Io's volcanic landscape, we travel outward to encounter Ganymede, Jupiter's largest moon, and indeed the largest moon in our entire solar system. Ganymede presents yet another face of cosmic diversity, combining ancient, heavily cratered terrain with younger, grooved regions that tell a story of geological evolution spanning billions of years. Ganymede is remarkable not only for its size, being larger than the planet Mercury, but also for possessing its own magnetic field. This makes Ganymede unique among moons, as it is the only satellite in our solar system known to generate its own magnetosphere. This magnetic field likely arises from motion in a liquid iron core, suggesting that Ganymede has a complex internal structure with distinct layers of different materials. The surface of Ganymede tells a story written in two distinct chapters. Dark terrain covers about 1/3 of the Moon's surface and appears to be very ancient, heavily scarred by impact craters accumulated over billions of years. This dark material may represent Ganymede's original crust, preserved from the early days of the solar system when impacts were much more frequent than they are today. The remainder of Ganymede's surface consists of lighter-colored terrain crossed by complex systems of ridges and grooves. This brighter terrain appears to be much younger than the dark regions, with far fewer impact craters to mark the passage of time. The formation of these grooved terrains likely involved some form of tectonic activity that reshaped large portions of the Moon's surface, though the exact mechanisms remain debated among planetary scientists. Some of the most striking features on Ganymede are the long, linear grooves that extend for hundreds of kilometers across the lighter terrain. These features suggest that Ganymede's icy crust has been stretched and fractured, possibly due to tidal forces from Jupiter or internal processes related to the differentiation of the Moon's interior. The regular spacing and parallel nature of many groove systems indicate that organized tectonic processes, rather than random impacts, were responsible for their formation. Like Europa, Ganymede likely harbors a subsurface ocean beneath its icy crust. Evidence for this hidden sea comes from observations of how Ganymede's magnetic field interacts with Jupiter's magnetosphere. The behavior of charged particles around Ganymede suggests the presence of a conducting layer beneath the surface, most likely a salty ocean that can carry electrical currents. Ganymede's subsurface ocean is thought to lie deeper beneath the surface than Europa's, sandwiched between layers of different types of ice formed under various pressure conditions. This multi-layered structure makes Ganymede's ocean less accessible than Europa's, but it also means that the ocean might be better protected from the harsh radiation environment around Jupiter. The complex internal structure of Ganymede, with its differentiated core, mantle, and multiple ice layers, suggests that this moon formed through a gradual process of accretion and heating. Unlike smaller moons that may have formed as single homogeneous bodies, Ganymede grew large enough and hot enough to separate into distinct layers based on density. This differentiation process would have released additional heat, possibly driving the tectonic activity that created the grooved terrain we observe today. Ganymede's magnetic field creates its own small magnetosphere, which carves out a cavity within Jupiter's much larger magnetic field. This interaction protects certain regions of Ganymede's surface from the most intense radiation, creating areas where future spacecraft could potentially operate with less risk of radiation damage. The magnetic field also generates auroras in Ganymede's thin oxygen atmosphere, similar to the northern and southern lights we observe on Earth. The thin atmosphere surrounding Ganymede consists primarily of oxygen, likely produced by the breakdown of water molecules on the Moon's surface due to radiation bombardment. This oxygen atmosphere is incredibly tenuous compared to Earth's, but it represents another similarity between Ganymede and our own planet, along with the magnetic field and possible subsurface ocean. Future exploration of Ganymede faces many of the same challenges as Europa missions, primarily the intense radiation environment around Jupiter. However, Ganymede's larger size and magnetic field provides some advantages for spacecraft operations. The magnetic field offers some protection from radiation, and the larger gravitational field makes it easier for spacecraft to enter stable orbits around the Moon. The European Space Agency's JUICE mission, launched in 2023, will extensively study Ganymede during the 2030s, including detailed mapping of its magnetic field, surface gratin, composition, and internal structure. This mission will help determine whether Ganymede's subsurface ocean exists and what conditions might prevail within it. Our exploration of Jupiter's major moons concludes with Callisto, the outermost of the 4 Galilean satellites discovered by Galileo Galilei in 1610. Callisto presents perhaps the most ancient face in the Jupiter system, its surface so heavily cratered that it appears to preserve a record of impacts dating back nearly to the formation of the solar system itself. Unlike its 3 inner siblings, Callisto shows little evidence of geological activity or surface renewal. Its dark, heavily cratered terrain suggests that this moon has remained largely unchanged for billions of years, making it a time capsule that preserves conditions from the early solar system. The density of impact craters on Callisto's surface is among the highest observed anywhere, indicating that the Moon's current surface is extremely old. Despite its ancient appearance, Callisto likely harbors secrets beneath its battered exterior. Like Europa and Ganymede, this distant moon may possess a subsurface ocean hidden beneath its icy crust. Evidence for this ocean comes from magnetic field measurements that suggest a conducting layer within Callisto's interior, most likely a salty ocean that can carry electrical currents generated by Jupiter's rotating magnetic field. The structure of Callisto's interior appears to be less differentiated than that of the other Galilean moons. While Ganymede clearly separated into distinct layers during its formation, Callisto seems to have remained more mixed, with ice and rock distributed throughout its interior rather than neatly separated by chemical density. This difference may be due to Callisto's greater distance from Jupiter, which would have resulted in less tidal heating during the Moon's early history. Callisto's surface composition reflects this mixed interior structure. Spectroscopic observations reveal a mixture of water ice and dark, rocky material distributed across the Moon's surface. The dark material may be carbonaceous compounds similar to those found in certain types of meteorites, suggesting that Callisto accreted from primitive materials that have remained largely unaltered since the solar crash system's formation. The most prominent feature on Callisto is Valhalla, a massive impact structure that spans nearly 4,000 kilometers across. This ancient impact basin consists of a bright central region surrounded by concentric rings of ridges and troughs that extend outward like ripples frozen in ice. Valhalla represents one of the largest impact structures in the solar system and provides insights into how large impacts affect icy bodies. The formation of Valhalla and similar impact structures on Callisto demonstrates that even relatively inactive worlds can be shaped by catastrophic events. The impact to the created Valhalla must have been enormous, possibly a large asteroid or comet that struck Callisto billions of years ago when such impacts were more common. The concentric ring structure suggests that the impact occurred in a relatively soft, icy target that could deform and flow in response to the massive energy release. Callisto's thin atmosphere consists primarily of carbon dioxide, likely produced by the sublimation of CO2 ice and the breakdown of carbonaceous materials on the surface due to radiation. Bombardment. This atmosphere is even thinner than Ganymede's, but it represents another piece of evidence for the complex chemistry occurring on apparently inactive worlds. The radiation environment at Callisto's distance from Jupiter is much less intense than that experienced by the inner Galilean moons. This makes Callisto an attractive target for future human missions to the Jupiter system, as spacecraft and eventually human explorers could operate there with less risk of radiation exposure. Callisto could potentially serve as a base of operations for exploring the Jupiter system, providing a relatively safe haven from which to launch missions to the more challenging environments closer to Jupiter. From our exploration of Jupiter's magnificent system of moons, we now continue outward to Saturn, where an entirely different family of satellites awaits our discovery. Saturn's moons present their own unique collection of mysteries and wonders, from the thick atmospheric shroud of Titan to the active geysers of Enceladus, and from the two-toned appearance of Iapetus to the strange sponge-like surface of Hyperion. Our first destination in the Saturnian system is Enceladus, a small, bright moon that has revolutionized our understanding of where life might exist in the outer solar system. From a distance, Enceladus appears as a pristine ball of fresh snow, reflecting nearly all the sunlight that reaches it from the distant sun. This high reflectivity, or albedo, indicates that Enceladus has a very young surface covered in clean, fresh ice. The secret of Enceladus lies in its south polar region, where a series of parallel cracks nicknamed tiger stripes cut across the moon's surface. These fissures are not merely surface features, but represent active fractures that extend deep into Enceladus's interior. From these cracks, enormous geysers erupt with tremendous force, shooting water vapor, ice crystals, and organic compounds hundreds of kilometers into space. The discovery of these geysers by the Cassini spacecraft in 2005 transformed our understanding of Enceladus from a small, presumably dead ice moon into one of the most promising places to search for life in our solar system. The material ejected by these geysers provides direct samples of what lies beneath Enceladus's frozen surface, offering a window into the moon's hidden interior without requiring a mission to land and drill through the ice. Analysis of the geyser material reveals that Enceladus harbors a global ocean beneath its icy shell, similar to Europa but more accessible due to the active venting occurring at the South Pole. This ocean contains dissolved salts, organic compounds, and other chemicals that suggest active hydrothermal processes occurring at the ocean floor. The chemistry of the expelled material includes hydrogen gas, which could serve as an energy source for microbial life similar to organisms found around Earth's deep-sea hydrothermal vents. The heat source driving Enceladus's geological activity appears to be tidal heating, similar to what powers the volcanoes of Io and maintains the oceans of Europa and Ganymede. However, Enceladus is much smaller than these other moons, making it surprising that tidal heating could generate enough energy to maintain active geology. The efficiency of this heating process on Enceladus suggests that the moon's orbit and internal structure are precisely tuned to maximize tidal dissipation, The tiger stripes themselves present fascinating geological features that provide clues about the processes occurring beneath the surface. These four parallel fractures, named Alexandria, Cairo, Baghdad, and Damascus, are warmer than their surroundings and show evidence of recent geological activity. The heat emanating from these features suggests that they represent direct connections between the subsurface ocean and the surface, allowing liquid water to reach areas where it can be ejected into space. The timing of geyser eruptions appears to be linked to Enceladus's orbital position around Saturn. When the Moon is farthest from Saturn in its slightly elliptical orbit, tidal forces are at their minimum, and the tiger stripes can open wider, allowing more material to escape. This orbital control of geological activity demonstrates the intimate connection between celestial mechanics and planetary geology. The composition of Enceladus's geysers has been analyzed in detail by multiple spacecraft flybys, revealing a complex chemistry that includes water vapor, ice grains, salt particles, and organic AB compounds. The presence of complex organic molecules suggests that the hydrothermal processes occurring in Enceladus's ocean may be creating the chemical building blocks necessary for life. While these organic compounds could form through non-biological processes, their detection makes Enceladus a high-priority target for astrobiological research. The global ocean beneath Enceladus's ice shell appears to be in direct contact with the Moon's rocky core, allowing for water-rock interactions that could provide essential nutrients and energy sources for potential berries. Life. This direct contact between ocean and rock is crucial because it enables the same types of hydrothermal processes that support life around Earth's deep-sea vents. The combination of liquid water, organic compounds, and chemical energy sources makes Enceladus one of the most habitable environments known beyond Earth. Future missions to Enceladus can take advantage of the active geysers to study the Moon's subsurface ocean without the need for complex drilling equipment. A spacecraft could fly through the geyser plumes and collect samples for detailed analysis, potentially detecting signs of life if it exists in the hidden ocean below. Such missions would need to be carefully designed to avoid contaminating this potentially life-bearing environment with Earth organisms. The discovery of active geology on Enceladus has implications beyond the search for life. This small moon demonstrates that geological activity can persist in the outer solar system, far from the Sun's warming influence, as long as appropriate energy sources are available. This realization has expanded our understanding of how many worlds might remain geologically active and potentially habitable, both in our own solar system and around other stars. From the active geysers of Enceladus, we travel to Titan, Saturn's largest moon and one of the most complex and Earth-like worlds in our solar system. Titan is unique among moons for possessing a thick atmosphere and active weather systems that create clouds, rain, rivers, and lakes on its surface. However, the liquid that flows across Titan's landscape is not water but liquid methane and ethane, creating an alien hydrological cycle unlike anything else we know. Titan's atmosphere is primarily composed of nitrogen, like Earth's, but it also contains significant amounts of methane and other hydrocarbons that give the Moon its distinctive orange haze. This thick atmosphere creates a substantial greenhouse effect that keeps Titan's surface temperature at a frigid -179 degrees Celsius, cold enough to freeze methane into liquid form, but warm enough to maintain a complex atmospheric system. The atmospheric pressure at Titan's surface is about 50% greater than Earth's atmospheric pressure at sea level, making Titan the only place in the solar system besides Earth where a human could walk around without a beanie. Pressure suit. Of course, the extreme cold and lack of oxygen would still require a full environmental suit, But the similarity in atmospheric pressure represents a remarkable parallel between these two worlds. Clouds form in Titan's atmosphere through processes remarkably similar to those that create clouds on Earth, but instead of water vapor condensing into water droplets, methane vapor condenses into methane quake, droplets that eventually fall as methane rain. This rain collects in rivers and lakes, creating surface features that would look familiar to Earth dwellers if not for their alien composition. The Cassini-Huygens mission provided our first detailed look at Titan's surface when the Huygens probe successfully landed in 2005. The descent through Titan's atmosphere revealed a landscape carved by flowing liquids with river channels, drainage networks, and what appeared to be shorelines marking ancient or seasonal lakes. The landing site showed a surface covered in water ice pebbles that had been rounded by liquid flow, providing direct evidence of active erosion and transport processes. Subsequent radar observations from the Cassini orbiter mapped Titan's entire surface, revealing a world shaped by processes remarkably similar to those that operate on Earth. River systems drain from highland regions into lowland basins, where they form lakes and seas of liquid hydrocarbons. The largest of these bodies, Kraken Mare, is larger than the Caspian Sea and contains more liquid hydrocarbons than all of Earth's oil reserves combined. The seasonal cycle on Titan drives changes in the distribution of surface liquids as methane and ethane evaporate from lakes in one hemisphere and condense in the other. Saturn's year lasts about 30 Earth years, so each season on Titan extends for more than 7 Earth years. Cassini observations documented how this seasonal cycle affects cloud formation, precipitation patterns, and lake levels, providing insights into the long-term stability of Titan's climate system. Beneath its hydrocarbon-rich surface, Titan likely harbors a subsurface ocean of liquid water, similar to those found on Europa, Ganymede, and Enceladus. This hidden ocean would be separated from the surface by a shell of water ice several tens of kilometers thick. The existence of this ocean is suggested by gravitational measurements, and by the way Titan responds to tidal forces from Saturn. The possibility of two separate environments for life on Titan presents a fascinating astrobiological puzzle. The surface environment, with its liquid hydrocarbons and complex organic chemistry, might support forms of life based on entirely different biochemistry than terrestrial organisms. Meanwhile, the subsurface water ocean might harbor more familiar forms of life similar to those that could exist in the oceans of other icy moons. Titan's thick atmosphere and active surface processes create a complex organic chemistry laboratory where countless chemical reactions produce increasingly complex molecules. The interaction between methane in the atmosphere and energetic radiation from the Sun and Saturn's magnetosphere drives the formation of complex hydrocarbons, nitriles, and other organic compounds that eventually settle to the surface as a kind of organic snow. This organic material accumulates over time, creating what scientists call tholins, complex organic polymers that give Titan its distinctive orange color. These tholins may preserve a record of atmospheric chemistry spanning millions of years, and they could potentially serve as raw materials for prebiotic chemistry if the right conditions arise. The study of Titan's organic chemistry provides insights into the types of chemical processes that may have occurred on the early Earth before life began. The landscape of Titan reveals features that demonstrate the power of liquid erosion in an alien environment. River channels meander across the surface, cutting through hills and depositing sediments in delta formations that closely resemble those formed by water on Earth. However, these channels are carved by liquid methane, which has very different physical properties than water, including lower density and viscosity that affect how it flows and erodes the landscape. Mountain ranges on Titan rise to heights of several kilometers, likely composed of water ice that is as hard as rock at Titan's frigid temperatures. These mountains may have formed through tectonic processes similar to those that create mountain ranges on Earth, driven by the same kinds of internal forces that shape terrestrial geology. The interaction between these ice mountains and the flowing hydrocarbons creates a geological environment unlike anywhere else in the solar system. Sand dunes stretch across vast equatorial regions of Titan, formed by winds that blow particles of organic material across the landscape. These dunes are remarkably similar in shape and size to sand dunes found in Earth's deserts, demonstrating that the fundamental physics of wind-driven sediment transport operates similarly even in Titan's alien environment. The organic particles that form these dunes are thought to be precipitated from the atmosphere as solid hydrocarbons settle out of the methane cycle. The polar regions of Titan host the largest concentrations of surface liquids, where vast lakes and seas of methane and ethane have accumulated over geological time. These bodies of liquid undergo seasonal changes, with some lakes appearing and disappearing as the distribution of hydrocarbons shifts between hemispheres. The northern polar region, which experiences summer during the current epoch, hosts the largest permanent bodies of liquid, while the southern polar region shows evidence of recently dried lake beds. Titan's magnetic environment is complex, influenced by its interaction with Saturn's powerful magnetic field. Unlike moons with their own magnetic fields, Titan does not generate its own magnetosphere, but its thick atmosphere and ionosphere create a complex electromagnetic environment that affects how charged particles from Saturn's radiation belts interact with the Moon's surface and atmosphere. The chemistry occurring in Titan's upper atmosphere creates a constant rain of organic compounds that have been accumulating on the surface for billions of years. This organic inventory may represent one of the largest reservoirs of complex carbon compounds in the solar system, providing a natural laboratory for studying the types of chemistry that could lead to the emergence of life under conditions very different from those on Earth. Future missions to Titan face the challenge of exploring both the surface environment and the potential subsurface ocean. Proposed concepts include floating probes that could sail across Titan's hydrocarbon seas, submarine vehicles that could explore their depths, and landers that could study the complex surface chemistry in detail. Such missions would need to operate in Titan's cold, chemically active environment while maintaining the ability to communicate across the vast distance to Earth. The study of Titan has revolutionized our understanding of atmospheric processes, surface geology, and organic chemistry in planetary environments. This remarkable moon demonstrates that complex, Earth-like processes can operate using entirely different materials under vastly different conditions, expanding our conception of what kinds of worlds might be capable of supporting interesting chemistry and potentially even life. From the complex atmospheric chemistry of Titan, we now turn to examine some of Saturn's stranger, smaller moons, each of which presents its own unique puzzles and characteristics. These worlds demonstrate the incredible diversity of small bodies that populate the outer solar system, shaped by different combinations of geological processes, impact history, and orbital dynamics. Iapetus, Saturn's third largest moon, presents one of the most striking visual appearances of any world in the solar system. This moon displays a stark two-toned coloration, with one hemisphere nearly as bright as fresh snow and the other as dark as charcoal. This dramatic contrast makes Iapetus appear almost like a giant yin-yang symbol floating in space, creating a mystery that has puzzled astronomers since the moon's discovery in Prey. 1671. The bright terrain on Iapetus consists primarily of relatively clean water ice, that reflects most of the sunlight reaching it from the distant sun. This bright material covers most of the trailing hemisphere, the side of the Moon that faces backward as Iapetus orbits Saturn. In contrast, the leading hemisphere is coated with dark material so effectively light-absorbing that it reflects only about 4% of incident sunlight, making it one of the darkest surfaces known in the solar system. The boundary between these light and dark regions is not gradual but remarkably sharp, creating a distinct dividing line that runs roughly along meridional lines across the Moon's surface. This sharp transition suggests that whatever process created the dark coating operated uniformly over large regions rather than gradually accumulating over time through random processes. The leading explanation for Iapetus's two-toned appearance involves the Moon's orbital characteristics and its interaction with Saturn's outer moon system. Iapetus orbits Saturn at a much greater distance than the other major moons, taking 79 days to complete one orbit compared to just 16 days for Titan. This distant orbit places Iapetus at the boundary between Saturn's regular satellite system and the realm of irregular satellites that likely represent captured asteroids and comets. The dark material coating Iapetus's leading hemisphere appears to be composed of organic compounds similar to those found on some asteroids and comets. One theory suggests that this material originated from Phoebe, Saturn's largest irregular satellite, which orbits in the opposite direction from most of Saturn's moons. Dust knocked off Phoebe by micrometeorite impacts could spiral inward under the influence of solar radiation pressure, eventually encountering Iapetus's orbit. As Iapetus moves through this cloud of dark particles, the leading hemisphere would preferentially accumulate the material, while the trailing hemisphere would remain relatively clean. Once this process began, it would become self-reinforcing because the dark material absorbs more heat from sunlight, causing localized warming that could drive the migration of ice from dark regions to bright regions, further concentrating the dark material and enhancing the contrast. Another remarkable feature of Iapetus is its equatorial ridge, a mountain range that extends more than halfway around the Moon's circumference and rises up to 20 kilometers above the surrounding terrain. This ridge gives Iapetus a distinctive walnut-like appearance and represents one of the most dramatic topographic features relative to body size anywhere in the solar system. The origin of Iapetus's equatorial ridge remains a subject of scientific debate. Some theories suggest it represents the remnant of a ring system that once surrounded the Moon and eventually collapsed onto its surface. Others propose that it formed through tectonic processes related to the Moon's early thermal evolution, or through the accumulation of debris from a disrupted satellite. The ridge's precise alignment with the Moon's equator suggests that its formation was controlled by Iapetus's rotation, but the exact mechanism remains uncertain. Hyperion presents an entirely different type of mystery among Saturn's moons. This irregularly shaped satellite tumbles chaotically through space, its rotation period varying unpredictably due to gravitational perturbations from Titan and other nearby moons. Hyperion's shape resembles a cosmic sponge or piece of pumice, with a surface covered in deep craters and holes that give it an extremely low density and unusual appearance. The chaotic rotation of Hyperion makes it unique among large moons in the solar system. Most satellites are tidally locked to their parent planets, always showing the same face as they orbit, but Hyperion's can't. Irregular shape and proximity to massive Titan create a complex gravitational environment that prevents stable synchronous rotation. Instead, the Moon tumbles unpredictably, sometimes completing a rotation in just a few days, and other times taking weeks. Hyperion's sponge-like appearance results from a combination of low density and impact cratering. The Moon appears to be composed largely of water ice with significant amounts of void space, giving it a density only slightly greater than liquid water. When impacts occur on such a low-density body, they tend to excavate material rather than creating the kind of raised rims and central peaks typical of craters on denser worlds. The surface of Hyperion shows a distinctive pattern of overlapping craters with steep walls and flat floors, creating a landscape unlike any other known world. Some of these craters contain dark material similar to that found on Iapetus, suggesting that organic compounds are common throughout Saturn's outer satellite system. The accumulation of this dark material in crater floors may be related to thermal processes that cause ice to sublimate from warmer, sun-facing surfaces and condense in cooler, shadowed regions. Pan, one of Saturn's smallest named moons, orbits within the Encke gap in Saturn's A ring and demonstrates how gravitational interactions between moons and ring particles can create complex orbital dynamics. This tiny moon, only about 28 kilometers across at its widest point, has swept clear a gap in the ring system through its gravitational influence. But the process has also created a distinctive equatorial ridge that gives Pan a flying saucer-like appearance. The ridge around Pan's equator consists of ring particles that have been captured by the Moon's gravity and accumulated over time. This process demonstrates how moons and ring systems interact, with small satellites acting as gravitational shepherds that control the distribution of ring material. The study of Pan and similar ring moons provides insights into how planetary ring systems evolve and how satellite systems form and migrate over time. Saturn's diverse family of moons showcases the incredible variety of worlds that can exist within a single planetary system. From the active geysers of Enceladus to the thick atmosphere of Titan, from the two-toned mystery of Iapetus to the chaotic tumbling of Hyperion. Each of these worlds tells a unique story of formation and evolution shaped by different combinations of orbital dynamics, internal structure, and external influences. As we prepare to leave the Saturn system and venture even further from the Sun, we reflect on how these distant moons have expanded our understanding of planetary science and astrobiology. The active geology of small, icy worlds like Enceladus has shown us that the traditional habitable zone around stars may be far too restrictive, and that life-supporting environments might exist in places Enceladus we never expected. Our journey now takes us beyond Saturn to the ice giant planets Uranus and Neptune, where we encounter satellite systems that are smaller and less well-studied than those of Jupiter and Saturn, but no less gaseous. Intriguing in their own ways, these distant worlds represent the frontier of our knowledge about moon systems, and they hint at the incredible diversity of satellites that may exist around planets throughout the universe. Uranus possesses a system of 27 known moons, most of which are named after characters from the works of William Shakespeare and Alexander Pope. The largest of these, Titania, Oberon, Umbriel, Ariel, and Miranda, were discovered in the 18th and 19th centuries, while the smaller satellites have been found more recently through improved telescopic observations and spacecraft missions. Miranda, the innermost and smallest of Uranus's major moons, presents one of the most geologically complex and puzzling surfaces known among small satellites. When Voyager 2 flew past Miranda in 1986, it revealed a world that appeared to have been assembled from mismatched pieces, with regions of different terrain types jumbled together in a patchwork pattern that defied easy explanation. The surface of Miranda displays three distinct types of terrain that seem almost randomly distributed across the Moon's face. Ancient, heavily cratered regions appear alongside younger, grooved terrains similar to those found on Ganymede, while strange, chevron-shaped features called coronae create patterns unlike anything seen elsewhere. In the solar system, these coronae consist of concentric ridges and valleys that form oval or polygonal shapes, suggesting some kind of organized geological process. The most striking feature on Miranda is Verona Rupes, a cliff that rises approximately 20 kilometers above the surrounding terrain, making it one of the tallest known cliff faces in the solar system. On a world with Miranda's low gravity, an object dropped from the top of this cliff would take about 10 minutes to reach the bottom, falling at a leisurely pace that would allow ample time to admire the scenery during the descent. The geological complexity of Miranda is surprising given the Moon's small size, only about 470 kilometers in diameter. Such a small world should have cooled quickly after its formation, becoming geologically inactive within a relatively short time. The presence of young-looking terrain and complex geological features suggests that Miranda experienced significant heating and geological activity long after its formation. One theory for Miranda's unusual appearance proposes that the Moon was once shattered by a massive impact that broke it apart into several large pieces. These pieces then reaccumulated under their mutual gravitational attraction, but not in their original configuration, creating the jumbled appearance we observe today. While this theory explains some aspects of Miranda's geology, it raises questions about how such a catastrophic disruption could occur and why the reassembled pieces which show evidence of subsequent carve geological activity. Alternative theories suggest that Miranda's complex geology results from tidal heating caused by orbital resonances with other Uranian moons. Even though these moons are much smaller than the Galilean satellites of Jupiter, gravitational interactions between them could have generated enough internal heating to drive geological activity on Miranda. This heating might have been episodic, occurring during periods when orbital resonances were particularly strong, explaining why some regions appear much younger than others. The other major moons of Uranus show evidence of their own geological histories, though none as dramatic as Miranda's. Ariel displays evidence of past geological activity in the form of extensional faults and smooth plains that appear to have been resurfaced by some form of cryovolcanism. Umbriel presents an ancient, heavily cratered surface that appears to have remained largely unchanged for billions of years, while Titania and Oberon show intermediate levels of geological modification. The composition of Uranian moons appears to be a mixture of rock and water ice, similar to many satellites in the outer solar system, but with some unique characteristics that reflect the different conditions in the ISE, Uranian system. These moons formed in an environment where water ice was abundant but rocky material was less concentrated than in the inner solar system, resulting in bodies with lower overall densities and different internal Bachi structures. Neptune's largest moon, Triton, stands out as one of the most unusual objects in the solar system due to its retrograde orbit, which means it travels around Neptune in the opposite direction from the gradar planet's rotation. This orbital characteristic strongly suggests that Triton was not formed in place, but was instead a captured object, likely a large Kuiper belt object that was gravitationally captured by Neptune during the crash. Early history of the solar system. The capture process that brought Triton into Neptune's orbit would have been a violent and disruptive event that likely destroyed any original satellite system Neptune may have possessed. The energy released during the capture process would have melted Triton's interior completely, allowing the Moon to differentiate into distinct layers and potentially driving geological activity that continued for millions or billions of years after the capture event. Triton's surface displays evidence of recent geological activity, with relatively few impact craters and a complex terrain of ridges, valleys, and smooth plains that suggest ongoing resurfacing processes. The Moon possesses a thin atmosphere composed primarily of nitrogen, similar to that of Pluto, which is consistent with the theory that Triton originated in the Kuiper Belt where nitrogen-rich objects are common deep current. One of the most remarkable discoveries about Triton came from Voyager 2 observations that revealed active nitrogen geysers erupting from the Moon's south polar region. These geysers shoot dark material up to 8 kilometers above the surface, demonstrating that geological activity continues on this distant world despite its location far from the Sun's warming influence. The mechanism driving Triton's geysers appears to be seasonal heating of the Moon's thin nitrogen atmosphere. As Neptune's orbital motion brings different regions of Triton's surface into sunlight, sublimation of nitrogen ice creates pressure that can drive explosive eruptions through weak points in the surface. The dark material carried by these geysers may consist of organic compounds produced by radiation processing of methane and other hydrocarbons in Triton's atmosphere and on its surface. Triton's retrograde orbit is gradually decaying due to tidal interactions with Neptune, meaning that the Moon is slowly spiraling inward toward its parent planet. In the distant future, perhaps 50 million years from now, Triton will pass within Neptune's Roche limit and be torn apart by tidal forces, potentially creating a spectacular ring system around Neptune that could rival or exceed Saturn's rings in extent and complexity. The study of Triton provides insights into the characteristics of Kuiper Belt objects and the processes that shaped the outer solar system during its early history. As the only large captured satellite we can study in detail, Triton serves as a representative of the population of icy bodies that formed in the outer reaches of the solar system and helps us understand the conditions and processes that operated in these distant regions. Beyond Neptune lies the realm of dwarf planets and small bodies that populate the Kuiper Belt and scattered disk regions of the outer solar system. While most of these objects are too small and distant to possess significant satellite systems, some do have moons that provide additional insights into the formation and evolution of the solar system's outermost regions. Pluto, the most famous dwarf planet, possesses a system of 5 known moons dominated by Charon, which is large enough relative to Pluto that the two objects form what is essentially a binary system. The Pluto-Charon system is tidally locked, with both objects always showing the same face to each other as they orbit their common center of mass. This synchronous rotation creates a unique dynamic in which Pluto and Charon appear fixed in each other's skies, never rising or setting from the perspective of observers on either world. The origin of the Pluto-Charon system likely involves a giant impact similar to the one thought to have created Earth's moon. A large object colliding with Pluto could have ejected material that subsequently coalesced to form Charon, explaining the high angular momentum of the system and the similar compositions of both objects. However, unlike the Earth-Moon system, Pluto-Charon appears to have achieved perfect tidal synchronization, with both objects locked in permanent gravitational embrace. The smaller moons of Pluto Nix, Hydra, Styx, and Kerberos likely formed from debris left over from the impact that created Charon. Or they may represent captured Kuiper Belt objects that were gravitationally bound to the Pluto-Charon system after its formation. These tiny moons follow complex orbital patterns influenced by the gravitational fields of both Pluto and Charon, creating a dynamically rich environment in the outer solar system. Other dwarf planets in the Kuiper Belt and scattered disk regions also possess moon systems that provide clues about conditions in the outer solar system. Eris, which is slightly more massive than Pluto, has one known moon called Dysnomia. Makemake and Haumea also have satellite systems that help astronomers determine the masses and densities of these distant objects, providing insights into their composition and formation history. The study of these distant moon systems represents the current frontier of solar system exploration, where new discoveries continue to expand our understanding of how planetary systems form and evolve. As our telescopes become more powerful and our spacecraft venture ever farther from the Sun, we continue to discover new moons and satellite systems that challenge our theories and expand our conception of the debris. Diversity possible in planetary systems. From our exploration of the solar system's most distant moons, we now turn our attention beyond the boundaries of our own stellar neighborhood to consider the moons that may exist around planets orbiting other stars. The search for exomoons represents one of the newest and most challenging frontiers in astronomy, requiring techniques and technologies that push the limits of our current observational capabilities. The detection of exomoons presents enormous technical challenges because these objects are much smaller and dimmer than their parent planets, which are themselves difficult to observe directly around distant stars. Most exoplanets are detected indirectly through their gravitational effects on their parent stars, or by the small dimming they cause when they pass in front of their stars as seen from Earth. Detecting moons requires finding even smaller signals buried within the noise of these already challenging observations. Several methods have been proposed for detecting exomoons, each with its own advantages and limitations. Transit timing variations look for small changes in the timing of planetary transits that could be caused by the gravitational pull of orbiting moons. As a planet and its moon orbit their common center of mass, the planet's position relative to the star changes slightly, causing small variations in the timing of transits that could potentially be detected by sensitive car instruments. Transit duration variations represent another approach, looking for changes in how long a planetary transit lasts as the planet-moon system moves through different orbital configurations. When a moon is positioned to add to the total cross-sectional area blocking starlight, the transit duration increases slightly, while the duration decreases when the moon's shadow falls outside the stellar disk. Direct detection of moon transits represents perhaps the most straightforward approach, looking for small additional dimming events that occur when moons pass in front of their parent stars separately from planetary T transits. However, this method requires moons that are large enough and positioned appropriately to create detectable signals, making it suitable only for the largest possible exomoons around planets with favorable plane orbital geometries. Gravitational microlensing offers another potential avenue for exomoon detection, taking advantage of the fact that massive objects bend light through their gravitational fields. When a star with planets and moons passes in front of a more distant star, the gravitational field acts as a natural telescope that magnifies and distorts the background star's light. Careful analysis of these lensing events could potentially reveal the presence of planetary satellites. The first tentative detections of exomoon candidates have begun to emerge from analysis of data from space-based telescopes like Kepler and TESS. These potential discoveries remain controversial and require confirmation through additional observations, but they suggest that moon systems around exoplanets may be common and detectable with current technology when conditions are favorable. The types of moons that might exist around exoplanets depend strongly on the characteristics of the planetary systems in which they form. Planets that migrate inward from their original formation locations, as appears to be common among exoplanets, might lose their original moon systems during the migration process. However, they could potentially capture new satellites from debris disks or through gravitational interactions with other objects in their systems. Hot Jupiters, gas giant planets that orbit very close to their parent stars present particularly interesting cases for exomoon studies. The intense radiation and tidal forces in these environments would likely strip away small moons, but large satellites might be able to survive if they formed or were captured after the planet reached its final path, orbit. Such moons would experience extreme conditions, with surface temperatures hot enough to melt rock and atmospheric compositions unlike anything found in our own solar system. Planets in the habitable zones of their stars, where liquid water could potentially exist on planetary surfaces, represent the most intriguing targets for exomoon searches from an astrobiological perspective. Large moons around such planets could potentially harbor their own atmospheres and surface conditions suitable for life, effectively doubling the number of potentially habitable worlds in each planetary system. The tidal interactions between exoplanets and their moons could create additional heating that might extend the habitable zone beyond its traditional boundaries, similar to how tidal heating keeps subsurface oceans liquid on moons like Europa and Enceladus. This tidal heating could potentially make moons around cold planets habitable, even when they receive little energy from their parent stars. The study of exomoons also provides insights into planetary system formation and evolution processes that may be common throughout the galaxy. By comparing moon systems around exoplanets with those in our own solar system, astronomers can test theories about how satellites form and how they influence planetary evolution over long time scales. Current and future space missions are expanding our capabilities for detecting and studying exomoons. The James Webb Space Telescope, with its unprecedented infrared sensitivity, may be able to detect the thermal emission from large exomoons or analyze their atmospheric compositions through transit. Spectroscopy. Ground-based telescopes with adaptive optics systems and advanced coronagraphic capabilities are also pushing toward direct imaging of exoplanetary systems where the largest moons might eventually be detectable. The search for exomoons represents more than just an academic exercise in pushing observational limits. These potential worlds could significantly expand the number of habitable environments in the galaxy, providing new targets for the search for life beyond Earth and new insights into the conditions that allow complex chemistry and potentially biology to flourish in planetary systems. As we develop more sensitive instruments and more sophisticated analysis techniques, the detection of exomoons will likely become routine, opening up entirely new fields of comparative satellite science. We may discover moon systems that are even more diverse and complex than those in our own solar system, with satellite architectures and dynamical interactions that we cannot currently imagine. The role of moons in planetary systems extends far beyond their value as individual worlds worthy of study. These satellites serve as crucial components in the gravitational architecture of planetary systems, influencing everything from planetary rotation and axial stability to the delivery of materials that may be essential for the development of life. The gravitational influence of moons helps stabilize the rotation axes of their parent planets, preventing the kind of chaotic axial wandering that would create extreme climate variations unsuitable for the development of complex life. Earth's moon provides an excellent example of this stabilizing influence, keeping our planet's axial tilt relatively constant over million-year timescales and ensuring that climate zones remain stable enough for evolutionary processes to operate. Without this lunar stabilization, Earth's rotational axis could tilt anywhere from nearly 0 degrees to more than 80 degrees relative to its orbital plane, creating a world where polar regions might alternately freeze and bake as they pointed toward or away from the sun. Such extreme variations would make it nearly impossible for ice caps to persist, ocean currents to remain stable, or ecosystems to develop the kind of long-term stability that appears necessary for the evolution of complex life. Mars provides a cautionary example of what can happen to a planet without adequate lunar stabilization. Mars has two tiny moons, Phobos and Deimos, but these satellites are far too small to provide significant rotational stability. As a result, Mars's rotational axis has wandered dramatically over geological time, swinging through variations of more than 60 degrees that have driven extreme climate changes throughout the planet's history. Evidence for this axial wandering on Mars comes from the distribution of water ice deposits, the orientation of ancient river channels, and the location of layered sedimentary deposits that indicate where polar regions were located during different epochs. These geological signatures tell a story of a world whose climate has been dominated by astronomical forces rather than the relatively stable conditions that have characterized Earth throughout most of its history. The delivery of water and other volatile materials to planetary surfaces may also depend critically on the presence of large moons. Impact simulations suggest that moons can act as gravitational focusing agents that increase the rate at which comets and asteroids strike planetary surfaces. While this might seem detrimental, the enhanced impact rate may actually be beneficial for delivering the water and organic compounds necessary for life to emerge. On early Earth, the Moon's gravitational influence may have helped focus comet impacts during the late heavy bombardment, a period about 4 billion years ago when the inner solar system experienced an intense barrage of impacts from outer solar system objects. These impacts likely delivered much of the water that filled Earth's oceans and may have brought organic compounds that served as raw materials for the first biological processes. The tidal forces generated by moons also play crucial roles in planetary evolution. On Earth, lunar tides have helped drive the mixing of ocean waters that distributes nutrients and maintains the chemical gradients necessary for biological processes. Tidal pools created by the regular rise and fall of sea levels may have provided the concentrated chemical environments where the first self-replicating molecules could form and evolve. In the outer solar system, tidal heating generated by large planets provides the energy source that keeps subsurface oceans liquid on moons like Europa, Enceladus, and possibly Titan. Without this tidal heating, these worlds would be completely frozen, eliminating any possibility for the liquid water environments that make them such promising targets for astrobiological research. The magnetic fields generated by some moons, like Ganymede's intrinsic magnetosphere, provide additional protection from harmful radiation that could otherwise sterilize planetary surfaces or thin R atmospheres. These magnetic shields complement the protection provided by planetary magnetic fields, creating safe havens where life could potentially flourish even in the radiation-intense environments around giant planets. Moons also influence the evolution of planetary atmospheres through various mechanisms. The impact gardening caused by small meteorites hitting airless moons can liberate gases that become part of thin exospheres, while larger impacts can eject material that may eventually reach planetary atmospheres. The volcanic outgassing from geologically active moons like Io contributes materials to planetary magnetospheres and may influence atmospheric chemistry on nearby worlds. The orbital dynamics of moon systems create complex gravitational environments that can trap dust and small particles, potentially protecting inner planets from bombardment while creating reservoir of material that could later be delivered to planetary surfaces when orbital configurations change. These dynamical effects operate over millions and billions of years, influencing planetary evolution in ways that we are only beginning to understand. As we search for potentially habitable exoplanets, the presence or absence of large moons may prove to be a crucial factor in determining which worlds could actually support life over the long timescales necessary for biological evolution. Planets without adequate lunar stabilization may be subject to climate variations too extreme for complex life to develop, while planets with large moons may enjoy the kind of stable conditions that can allow biology to flourish. The study of moon formation processes also provides insights into the violent early history of planetary systems. The giant impact hypothesis for lunar formation suggests that the early solar system was a much more chaotic place than it is today, with planet-sized objects colliding and merging in catastrophic events that shaped the final architecture of planetary systems. Similar impact events may have occurred throughout the galaxy as other planetary systems formed, suggesting that large moons created by giant impacts might be relatively common around terrestrial planets. The search for such moons around exoplanets could provide tests of planetary formation theories and help us understand whether Earth-like worlds with large stabilizing satellites are common or rare in the galaxy. The chemical composition of moons provides additional clues about the materials and processes that were available during planetary system formation. Moons that formed from impact debris preserve samples of both the target planet and the impacting object, creating natural museums that record the composition and characteristics of the planetary building blocks that existed billions of years ago. Analysis of lunar samples returned by Apollo missions has revealed that the Moon contains materials with isotopic signatures that are nearly identical to Earth's mantle, supporting the giant impact hypothesis and providing constraints on the composition and origin of the impacting object. Similar analyses of samples from other moons could reveal the diversity of materials that went into building different planetary systems. The future of lunar and satellite science promises even more exciting discoveries as new missions venture to previously unexplored worlds and as new technologies enable more detailed studies of familiar objects. Proposed missions to Europa, Enceladus, Titan, and other potentially habitable moons could revolutionize our understanding of astrobiology and the conditions necessary for life to emerge and survive. Advances in computational modeling are also helping scientists understand the complex interactions between moons, planets, and their environments. Sophisticated simulations can now model tidal heating, orbital evolution, and atmospheric escape processes with unprecedented accuracy, providing new insights into how moon systems evolve over billions of years. The development of more powerful telescopes, both ground-based and space-based, continues to push the boundaries of what we can observe in our own solar system and beyond. Future instruments may be capable of detecting atmospheric compositions on exomoons, measuring their surface temperatures, and even identifying potential biosignatures in their spectra. As we stand at the threshold of a new era in planetary science, the study of moons continues to reveal the incredible complexity and beauty of the universe around us. These worlds, once thought to be simple, dead objects orbiting their parent planets, have proven to be dynamic, diverse, and potentially life-bearing environments that challenge our understanding of habitability and expand our conception of where life might exist. The moons we have explored in our journey tonight represent just a small fraction of the satellites that exist in our own solar system, and an even smaller fraction of the moons that likely populate the galaxy as a whole. Each new discovery brings fresh mysteries and unexpected revelations that remind us how much we still have to learn about the cosmic environment in which we live. From the familiar face of Earth's moon that has guided human civilization for millennia, to the alien geysers of Enceladus that shoot ice crystals hundreds of miles into space, from the methane lakes of Titan to the Titan, volcanic fury of Io. The moons of our solar system showcase the incredible diversity of worlds that can exist when matter organizes itself under the influence of gravity and the other fundamental forces of nature. These worlds remind us that the universe is far stranger and more wonderful than we might ever have imagined. In places where we expected to find only cold, dead rock and ice, we have discovered active geology, complex chemistry, and environments that may harbor the ingredients necessary for life itself. The subsurface oceans hidden beneath the icy crusts of Europa, Enceladus, and Ganymede may contain more habitable volume than all the surface waters of Earth. The moons we have encountered challenge us to expand our definition of habitability beyond the narrow concept of surface liquid water in a planet's habitable zone. Tidal heating can maintain liquid environments far from the warmth of stars, and complex organic chemistry can operate under conditions vastly different from those that support life on Earth. These realizations have profound implications for our understanding of how common life might be in the universe. As we look toward the future, the continued exploration of moons in our own solar system and the search for exomoons around distant planets promise to reveal even more about the role these objects play in creating and maintaining the tania, conditions necessary for life. The moons that have fascinated humanity since we first looked up at the night sky continue to hold secrets that may unlock fundamental questions about our place in the cosmos. The story of moons is ultimately a story about the intimate connections between celestial objects and the delicate gravitational dances that shape entire worlds. These satellites serve as constant reminders that no world exists in isolation, but rather as part of complex systems where every component influences every other component in ways both subtle and profound. In the gentle light of Earth's moon that bathes our world each night, in the hidden oceans that may teem with alien life beneath sheets of ice billions of miles away, in the volcanic fires that paint the darkness around Jupiter, and in the methane rains that fall on Titan's alien shores, we find reflections of the incredible richness and complexity that emerges when matter and energy interact under the governance of natural law. These worlds invite us to continue exploring, to keep asking questions, and to never lose our sense of wonder at the incredible diversity and beauty of the universe we inhabit. As long as moons continue to orbit planets, and as long as humans retain their curiosity about the cosmos, these mysterious worlds will continue to inspire us with their secrets and their stories, written in stone and ice across the vast expanse of space and time. Our journey through the realm of mysterious moons now brings us to the peculiar satellites of Mars, worlds that tell a different story entirely from the large, gravitationally significant moons we have encountered around the Bender. Giant planets. Phobos and Deimos, named after the Greek gods of fear and panic who accompanied Ares into battle, are among the smallest and most unusual moons in our solar system, raising questions about their origin that continue to puzzle planetary scientists today. Phobos, the larger and inner of Mars's two moons, measures only about 27 kilometers at its widest point, making it roughly the size of a small city. This tiny world orbits so close to Mars that it completes 3 full orbits in a single Martian day, racing across the Martian sky in a matter of hours rather than the weeks or months typical of most moons. From the surface of Mars, Phobos would appear to rise in the west and set in the east, moving visibly across the sky during the course of an observation session. The surface of Phobos is dominated by a single enormous crater called Stickney, which stretches nearly 10 kilometers across and represents a collision so violent that it nearly shattered the tiny moon entirely. The impact that created Stigny must have delivered a tremendous shock to Phobos, and indeed, the moon's surface shows a network of grooves and fractures that may represent damage from this catastrophic event. Some of these grooves extend for kilometers across the surface, creating linear patterns that give Phobos a distinctly battered appearance. The composition and density of Phobos suggests that it may not have formed in orbit around Mars at all, but rather represents a captured asteroid that was gravitationally snared by the red planet sometime in the distant past. Spectroscopic observations reveal that Phobos has a very dark surface with reflective properties similar to certain types of carbon-rich asteroids found in the outer regions of the asteroid belt. This composition is quite different from what we might expect for a moon that formed from the same materials as Mars. Deimos, the outer and smaller moon, presents an even more extreme example of a captured asteroid. At only about 15 kilometers across, Deimos is roughly half the size of Phobos and follows a more distant orbit that takes about 30 hours to complete. Unlike Phobos with its dramatic crater and fractured surface, Deimos has a relatively smooth appearance, though it is still heavily cratered on smaller scales. The origin of Mars's moons remains an active area of research and debate. The capture hypothesis suggests that both Phobos and Deimos were originally asteroids that wandered too close to Mars and were gravitationally captured into orbit around the planet. However, asteroid capture is an extremely difficult process that requires very specific conditions to occur. Most objects that approach a planet closely are either deflected away by gravitational interactions or crash directly into the planetary surface. For successful capture to occur, the approaching asteroid must lose energy through some mechanism that allows it to become gravitationally bound to the planet. Possible mechanisms include atmospheric drag, if the planet possesses a thick atmosphere, or three-body interactions involving other objects in the system. Mars's thin atmosphere seems insufficient to capture objects as large as Phobos and Deimos, and the lack of other large moons makes three-body capture scenarios difficult to construct. An alternative theory proposes that Phobos and Deimos formed from debris created by a large impact on Mars, similar to the giant impact hypothesis for Earth's moon. In this scenario, a massive asteroid or comet struck Mars early in its history, ejecting material that eventually coalesced to form the two small moons. This impact formation hypothesis could explain why the moons have compositions somewhat similar to Mars, while still accounting for their unusual orbital characteristics. Recent detailed studies of Phobos have revealed additional mysteries about its internal structure and composition. The moon's density is much lower than expected for solid rock, suggesting that it may be largely hollow or composed of very porous rubble pile material held together primarily by its own weak gravity. This low density supports the idea that Phobos formed through accretion of debris rather than as a single, solid object. The orbital evolution of Mars's moons presents fascinating dynamics that will play out over geological timescales. Phobos is gradually spiraling inward toward Mars due to tidal interactions with the planet, losing altitude at a rate of about 2 meters per century. In approximately 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces when it passes within the planet's Roche limit, potentially creating a temporary ring system around the A-tree, red planet. Deimos, being farther from Mars, experiences the opposite effect and is slowly moving outward, eventually destined to escape Mars's gravitational influence entirely and become an independent object, orbiting the Sun. This divergent evolution of the two moons provides a natural experiment in orbital mechanics and tidal interactions that helps scientists understand how satellite systems evolve over long time periods. The grooves and fractures on Phobos's surface have been the subject of intense study and speculation. While some of these features clearly result from the Stickney impact, others may be related to tidal stresses caused by Phobos's close orbit around Mars. As the Moon orbits, it experiences varying gravitational forces that could create internal stresses sufficient to fracture the surface, especially if Phobos is indeed a loosely consolidated rubble pile, as its low Carl density suggests. Future missions to Mars's moons could provide definitive answers about their origin and composition. Several space agencies have proposed sample return missions that would land on Phobos or Deimos, collect material from their surfaces, and return it to Earth for detailed analysis. Such missions would be technically challenging due to the extremely low gravity of these tiny worlds, but they would provide invaluable insights into the formation and evolution of small satellites. The Japan Aerospace Exploration Agency's MMX Martian Moons E-exploration mission, currently in development, plans to visit both Phobos and Deimos, collect samples from Phobos, and return them to Earth for analysis. This mission will help determine whether Mars's moons are captured asteroids, impact-formed debris, or perhaps something else entirely. The study of Phobos and Deimos also provides insights into the broader population of small moons and captured objects throughout the solar system. Many of the outer planets possess irregular satellites that show clear signs of being captured asteroids or comets, and understanding how such capture processes work helps scientists reconstruct the early history of planetary system formation. The irregular satellites of the giant planets present their own fascinating stories of capture and evolution. Jupiter possesses more than 70 known moons, many of which are small, irregularly shaped objects with highly elliptical orbits that carry them far from the planet before bringing them back close to the Jovian cloud tops. These distant satellites often travel in retrograde orbits, moving opposite to Jupiter's rotation, which is a clear signature of capture rather than in situ formation. Saturn's irregular satellite system includes Phoebe, a dark object that may represent a captured Kuiper Belt object or centaur that wandered into the inner solar system and was gravitationally snared by Saturn B12. Phoebe's composition includes water ice mixed with dark organic compounds, giving it characteristics similar to comets and outer solar system objects. The retrograde orbit and composition of Phoebe support the idea that it originated far from Saturn and was captured relatively recently in astronomical terms. The irregular satellites of Uranus and Neptune tell similar stories of capture, with many showing characteristics that suggest they formed in the outer solar system and were subsequently captured by their current parent planets. These capture events may have occurred during periods of dynamical instability in the early solar system, when planetary orbits were still evolving and interactions between planets could scatter objects throughout the outer regions. The study of captured satellites provides insights into the migration history of the giant planets and the dynamical evolution of the early solar system. Computer models suggest that Jupiter, Saturn, Uranus, and Neptune did not form in their current orbits, but instead migrated inward and outward over millions of years as they interacted gravitationally with the disk of debris left over from planetary formation. During these migration episodes, the giant planets would have encountered numerous small objects that could potentially be captured as irregular satellites. The characteristics of current irregular satellite populations provide constraints on planetary migration models and help scientists understand how the architecture of our solar system evolved to its present configuration. The captured moons also serve as accessible samples of primitive solar system material that would otherwise require expensive and technically challenging missions to asteroids or comets. By studying the compositions and characteristics of irregular satellites, scientists can learn about the materials and conditions that existed in different regions of the early solar system. Some irregular satellites may even preserve organic compounds and water ice that could provide insights into the delivery of volatile materials to the inner planets during the early bombardment period. If these moons represent captured comets or asteroid-like objects, they could contain the same types of materials that may have delivered water and organic compounds to Earth billions of years ago. The gravitational influence of irregular satellites on their parent planets is generally negligible due to their small sizes and distant orbits, but they can interact with each other in complex ways that lead to orbital evolution over long timescales. Some irregular satellites exist in groups with similar orbital characteristics, suggesting that they may be fragments of larger objects that were broken apart by collisions after being captured. The Himalaya group at Jupiter and the Inuit group at Saturn represent examples of such collisional families, where several small moons follow similar orbits that suggest a common origin through the breakup of a prefer. Larger parent body. The study of these satellite families provides insights into the collisional evolution of small bodies in planetary systems and the processes that create debris through mutual impacts. As our observational capabilities improve, we continue to discover new irregular satellites around the giant planets, with the current count exceeding 200 known objects across all 4 outer planets. Each new discovery adds to our understanding of capture processes and provides additional constraints on models of early solar system evolution. The search for irregular satellites has been greatly aided by advances in digital imaging and automated search algorithms that can identify faint, moving objects in astronomical images. Ground-based telescopes equipped with large-format digital cameras can now survey vast areas of sky around the giant planets, looking for the subtle motion that would indicate the presence of previously unknown moons. These observational programs have revealed that the irregular satellite systems of the giant planets are much richer and more complex than previously realized. The discovery of new moons continues at a steady pace, with several new objects being identified each year around Jupiter and Saturn in particular. The study of moon formation processes, from the giant impacts that may have created large regular satellites to the capture mechanisms that populate irregular satellite systems, provides crucial insights into the broader processes of planetary system formation and evolution. These mechanisms operate not only in our own solar system but also around exoplanets throughout the galaxy, suggesting that complex satellite systems may be common features of planetary systems. The diversity of moon formation mechanisms also suggests that satellite systems around exoplanets may be extremely varied, with some resembling our own solar system's regular satellite systems and others dominated by captured objects or formed through entirely different processes. This diversity has important implications for the habitability of exomoon systems and the likelihood of finding life-supporting environments around distant planets. As we continue our exploration of the most mysterious moons in the universe, we are reminded that even the smallest and most seemingly insignificant satellites can provide profound insights into the history and evolution of planetary systems. The tiny, battered worlds orbiting Mars, the distant, irregular satellites of the giant planets, and the complex orbital dynamics that govern their movements all contribute to our understanding of the cosmic processes that have shaped our solar system and continue to operate throughout the universe. The gravitational interactions that capture asteroids and comets as irregular satellites, the impact events that create families of related objects, and the tidal forces that drive orbital evolution all represent fundamental processes that operate wherever matter comes under the influence of gravity. By studying these processes in our own solar system, we develop the theoretical frameworks and observational techniques necessary to understand satellite systems around other stars and to predict the characteristics of moon systems we have yet to discover. The mysterious moons we have encountered in our journey represent far more than isolated curiosities scattered throughout the solar system. They are integral components of a complex, interconnected system of gravitational interactions that has evolved over billions of years and continues to evolve today. Each moon tells part of a larger story about planetary formation, the delivery of materials throughout planetary systems, and the creation of environments where life might potentially emerge and thrive. From the stabilizing influence of Earth's large moon to the tidal heating that maintains subsurface oceans on Europa and Enceladus. From the volcanic activity that resurfaces Io to the complex atmospheric chemistry occurring on Titan, from the captured asteroids orbiting Mars to the distant irregular satellites of the giant planets, we see a universe where moons play crucial roles in creating and maintaining the conditions that make planetary systems dynamic, diverse, and potentially life-supporting. As we stand at the beginning of a new era in the exploration of planetary systems, both within our own solar system and around distant stars, the study of moons will continue to provide fundamental insights into some of the most important questions we can ask about our place in the universe. Are we alone? How common are the conditions that allow life to emerge and evolve? What role do the complex gravitational interactions within planetary systems play in creating and maintaining habitable environments? The answers to these questions may ultimately be found not on planets themselves, but on the moons that orbit them, in the hidden oceans beneath icy crusts, in the complex chemistry of thick atmospheres, and in the delicate gravitational dances that create the stability necessary for life to flourish over the vast timescales required for evolution to produce complexity and intelligence. The mysterious moons of our universe continue to beckon us forward, inviting us to explore their secrets and to discover what they might teach us about the incredible richness and complexity of the cosmic subala. Environment we inhabit. In their silent orbits around distant worlds, in the ancient stories written in their cratered surfaces, and in the active geology that continues to reshape their landscapes, we find reflections of the fundamental forces and processes that govern the evolution of matter and energy throughout the cosmos. Each moon we encounter expands our understanding of what is possible when gravity, chemistry, and time interact to create worlds of stunning beauty and complexity. From the familiar companion that lights our earthly nights, to the alien landscapes of distant satellites where methane rains fall and ice volcanoes erupt, these worlds remind us that the universe is far stranger, more diverse, and more wonderful than we could ever have imagined when we first turned our eyes toward the stars and wondered what secrets they might hold. As our journey through the mysterious moons of the universe draws toward its close, we carry with us the knowledge that we have barely begun to scratch the surface of what these worlds have to teach us. Future missions will reveal new secrets, new discoveries will challenge our theories, and new questions will emerge to drive further exploration and understanding. The moons that have fascinated humanity since the dawn of consciousness will continue to inspire wonder, curiosity, and the insatiable desire to explore that drives us ever outward into the cosmic dark, seeking answers to the eternal questions about our origins, our destiny, and our place in the vast and magnificent universe we call home. The technological challenges of exploring these distant worlds have driven innovations that benefit humanity in countless ways. The development of spacecraft capable of surviving the radiation environment around Jupiter led to advances in DIA, radiation-hardened electronics that now protect satellites in Earth's orbit and enable medical devices to function reliably in harsh environments. The precision navigation required to thread spacecraft between the moons of Saturn has improved our ability to track objects in Earth's vicinity, enhancing our planetary defense capabilities against potentially hazardous asteroids. The instruments designed to analyze the composition of moon surfaces from millions of kilometers away have revolutionized our understanding of materials science and remote sensing. Spectrometers, originally built to study the icy surfaces of Europa, now help doctors diagnose diseases by analyzing tissue composition. Camera systems designed to image the methane lakes of Titan have found applications in autonomous vehicles navigating Earth's roads. The extreme environments encountered on these alien moons push the boundaries of our engineering capabilities and expand our understanding of what is possible under the most challenging conditions. The development of systems capable of operating at the temperatures found on Triton, where nitrogen freezes solid, has led to advances in cryogenic technology with applications ranging from medical preservation to quantum computing. The communication systems required to send signals across the vast distances of the outer solar system have driven innovations in data compression, error correction, and antenna design. These technologies now enable global communication networks that connect every corner of our planet and allow us to share the discoveries made at distant worlds with people everywhere. The power systems developed for spacecraft exploring the outer solar system, where solar panels become ineffective due to the dim sunlight, have advanced our understanding of radioisotope thermoelectric generators and nuclear power systems. These technologies provide clean, reliable energy for remote installations on Earth and offer pathways towards sustainable power generation for future human settlements beyond our planet. The life support and environmental control systems designed for potential missions to the moons of the outer planets have applications in extreme environments on Earth, from polar research stations to deep ocean exploration vehicles. The closed-loop systems that recycle air and water for long-duration space missions have inspired more efficient resource utilization in terrestrial applications, contributing to sustainable development and environmental protection. The study of tidal heating on moons like Io and Europa has advanced our understanding of geophysics and helped scientists better predict earthquakes and volcanic eruptions on Earth. The models developed to explain how gravitational forces generate heat within planetary bodies have applications in understanding the thermal evolution of our own planet and predicting the behavior of geothermal energy systems. The atmospheric models developed to understand the complex weather patterns on Titan have contributed to climate science on Earth, providing insights into how thick atmospheres respond to external forcing and how chemical cycles interact with meteorological processes. These models help scientists predict how Earth's climate might respond to changing conditions and inform strategies for mitigating climate change. The search for life in the subsurface oceans of icy moons has driven advances in astrobiology that are revolutionizing our understanding of life on Earth. The study of extremophile organisms that might survive in the high-pressure, low-temperature environments found beneath Europa's ice has led to the discovery of new forms of life in Earth's deep ocean and polar regions. These discoveries expand our understanding of the limits of life and suggest that biological processes might be more resilient and adaptable than previously thought. The techniques developed to detect organic compounds in the plumes of Enceladus are finding applications in environmental monitoring on Earth, allowing scientists to detect trace amounts of pollutants and biological markers in air and water samples. These sensitive detection methods help protect human health and monitor the effectiveness of environmental cleanup efforts. The gravitational analyses used to map the internal structures of moons like Ganymede and Callisto have improved our understanding of Earth's interior and helped geologists locate underground resources more efficiently. The same mathematical techniques that reveal the presence of subsurface oceans on distant moons can identify groundwater reserves and oil deposits beneath Earth's surface. The impact crater studies conducted on airless moons provide crucial data for understanding the bombardment history of the inner solar system and assessing the threat posed by near-Earth asteroids. By studying the size and frequency of craters on various moons, scientists can calibrate models of impact rates and better predict when Earth might face significant asteroid impacts. The formation mechanisms proposed for different types of moons have broad applications in understanding planetary formation processes throughout the galaxy. The insights gained from studying how satellites fall around giant planets inform our understanding of how planetary systems develop around other stars and help predict the characteristics of exoplanet systems that might harbor habitable worlds. The orbital dynamics calculations required to understand complex moon systems like those around Saturn have applications in satellite constellation design, space debris tracking, and mission planning for Dashen. Future exploration. The mathematical techniques developed to predict the long-term evolution of satellite orbits help ensure that Earth's orbital environment remains safe and accessible for future generations. The material science discoveries made through the study of moon compositions have led to the development of new alloys, ceramics, and composites with applications in aerospace, electronics, and construction. Understanding how materials behave under the extreme conditions found on various moons has expanded the range of environments where human technology can operate reliably. The robotic technologies developed for moon exploration, from precision landing systems to autonomous sample collection devices, have applications in terrestrial robotics, from surgical procedures to hazardous material handling. The artificial intelligence systems designed to operate spacecraft autonomously during the long communication delays to the outer solar system have contributed to advances in machine learning and autonomous systems. The psychological and social aspects of long-duration missions to distant moons have informed research into human factors for extended space exploration and have applications in understanding how people cope with isolation and stress in extreme environments on Earth. These insights contribute to better design of polar research stations, submarine crews, and other situations where small groups of people must work together in challenging conditions for extended periods. The international cooperation required for major moon exploration missions has strengthened diplomatic relationships and created frameworks for peaceful collaboration in space that serve as models for Baal. Addressing global challenges on Earth. The shared sense of wonder and discovery that comes from exploring these alien worlds helps unite humanity around common goals and shared values. The educational impact of moon exploration extends far beyond the scientific community, inspiring students around the world to pursue careers in science, technology, engineering, and mathematics. The dramatic images and fascinating discoveries from missions to Europa, Titan, and other moons capture the imagination and demonstrate the power of human curiosity and ingenuity to unlock the secrets of the universe. The philosophical implications of discovering potentially habitable environments on moons throughout the solar system challenge our understanding of our place in the cosmos, and our responsibilities as cosmic citizens. The possibility that life might exist in the hidden oceans of Europa or in the hydrocarbon lakes of Titan forces us to grapple with fundamental questions about the nature and value of life in all its possible forms. The economic benefits of moon exploration, while harder to quantify than technological spin-offs, include the development of new industries, the creation of high-skilled jobs, and the potential for resource utilization that could support future human expansion into the solar system. The water ice discovered on many moons could provide fuel and life support for future missions, while the rare materials found in some satellite compositions could have immense value for advanced technologies. The environmental perspective gained from studying the diverse climates and atmospheric processes on various moons provides crucial context for understanding Earth's environment and the factors that make our planet habitable. By studying worlds where greenhouse effects have run away, where atmospheres have been stripped away by solar wind, or where surface conditions are dominated by exotic chemistry, we gain appreciation for the delicate balance that maintains Earth's habitability. The long-term survival of human civilization may ultimately depend on our ability to expand beyond Earth and establish self-sustaining settlements on other worlds. The moons of the outer solar system, with their abundant water ice and diverse chemical inventories, could serve as stepping stones for human expansion into the galaxy. The knowledge gained from studying these worlds now will be essential for future generations who may call them home. The search for life beyond Earth represents one of the most profound scientific endeavors in human history, with implications that extend far beyond academic research. The discovery of life on Europa, Enceladus, or any other moon would fundamentally alter our understanding of biology, evolution, and our cosmic significance. Even if such life differs radically from terrestrial biology, its existence would demonstrate that the universe is far more biologically rich than currently understood. The study of prebiotic chemistry on moons like Titan provides insights into the processes that may have led to the emergence of life on Earth billions of years ago. By observing these chemical processes operating in real time on alien worlds, scientists can test theories about how complex organic molecules form and evolve under different environmental conditions. The magnetic field interactions observed around moons like Ganymede and the plasma physics occurring in the magnetospheres of giant planets contribute to our understanding of space weather and its effects on technological systems. This knowledge helps protect satellites, power grids, and communication systems from the effects of solar storms and geomagnetic disturbances. The geological processes operating on various moons provide natural laboratories for studying phenomena that are difficult to observe or reproduce on Earth. The cryovolcanism on Europa and Enceladus offers insights into how materials behave at extremely low temperatures, while the sulfur volcanism on Io provides data about chemical processes that occurred on the early Earth when volcanic activity was much more intense. The seasonal changes observed on moons like Titan, where weather patterns shift over decades-long cycles, provide insights into long-term climate dynamics but are difficult to study in Earth's more rapid climate system. These observations help scientists understand how planetary atmospheres respond to changes in solar input and how feedback mechanisms can amplify or dampen climate variations. The tidal interactions between moons and their parent planets create natural experiments in gravitational physics that test our understanding of celestial mechanics and general relativity. The precise measurements of orbital evolution and tidal dissipation in these systems provide data that can be used to refine theoretical models and test fundamental physical principles. The diverse surface compositions found on different moons reflect the varied environments and processes that operated during the formation of the solar system. By studying these compositional differences, scientists can reconstruct the temperature and chemical gradients that existed in the early solar nebula and understand how materials were distributed as planets, moons formed. The impact of moon exploration on human culture extends beyond scientific knowledge to influence art, literature, philosophy, and our collective imagination. The images of alien landscapes, the possibility of life in hidden oceans, and the vastness of space revealed through these missions inspire creative works that help humanity process and integrate these profound discoveries. The development of technologies for exploring moons in extreme environments drives innovation that benefits life on Earth in countless ways. From the materials that must withstand the radiation around Jupiter to the power systems that must operate in the perpetual cold of the outer solar system, each technological challenge overcome in the pursuit of moon exploration creates capabilities that find applications in terrestrial industries and improve human welfare. The international nature of many moon exploration missions demonstrates humanity's capacity for cooperation and shared achievement in the face of the most challenging endeavors. The complex logistics of coordinating missions involving multiple space agencies, the sharing of data and expertise across national boundaries, and the common sense of wonder that transcends political divisions all contribute to a more unified human perspective on our cosmic heritage. The timeline for future moon exploration stretches across decades and involves increasingly sophisticated missions that will revolutionize our understanding of these worlds. Planned missions to Europa will search for direct evidence of life in its subsurface ocean, while proposed expeditions to Titan will explore its complex organic chemistry and potentially land on the shores of its methane lakes. The technical challenges of landing on small, irregularly shaped moons with virtually no atmosphere require innovative solutions that push the boundaries of aerospace engineering. The development of autonomous navigation systems, precision landing technologies, and surface operations capabilities for these extreme environments drives advances that benefit all forms of space exploration. The sample return missions planned for various moons will bring pieces of these alien worlds back to Earth for detailed analysis in terrestrial laboratories. These samples will provide unprecedented insights into the composition, structure, and history of their parent bodies, potentially revealing evidence of past or present life and expanding our understanding of the chemical processes that operate throughout the solar system. The establishment of communication networks that can relay data from the outer solar system back to Earth requires advances in deep space communication technology that have applications for interstellar exploration and terrestrial communications. The development of more powerful transmitters, more sensitive receivers, and more efficient data compression algorithms benefits all forms of long-distance communication. The psychological preparation required for crew members on potential human missions to distant moons involves research into human performance, team dynamics, and mental health during extended isolation that has applications for terrestrial situations involving high stress and limited resources. These studies contribute to better understanding of human resilience and adaptation in extreme environments. The life support systems required for human missions to moons in the outer solar system must operate reliably for years or decades with minimal resupply from Earth. The development of closed-loop environmental control systems, advanced recycling technologies, and sustainable food production methods has applications for sustainable living on Earth and for future space settlements. The energy requirements for missions to distant moons drive the development of more efficient propulsion systems, advanced nuclear power technologies, and innovative energy storage solutions. These technologies have terrestrial applications in clean energy generation, transportation, and power grid management. The scientific instruments developed for moon exploration continue to become more sophisticated, miniaturized, and capable of autonomous operation. These advances benefit terrestrial science by providing better tools for environmental monitoring, medical diagnosis, materials analysis, and fundamental research across all scientific disciplines. The data analysis techniques required to process the vast amounts of information returned by moon exploration missions drive advances in artificial intelligence, pattern recognition, and data mining that have applications across all fields of human endeavor. The ability to extract meaningful patterns from complex datasets benefits everything from medical research to financial analysis. The public engagement and education programs associated with moon exploration missions inspire the next generation of scientists, engineers, and explorers while promoting scientific literacy and, quote, critical thinking skills throughout society. The sense of wonder and discovery generated by these missions helps maintain public support for science and technology advancement. The philosophical questions raised by moon exploration about the nature of life, the possibility of intelligence elsewhere in the universe, and humanity's role as cosmic explorers contribute to ongoing discussions about ethics, meaning, and purpose that transcend scientific boundaries and influence human culture and values. The long-term vision of human expansion into the solar system, enabled by the knowledge gained through moon exploration, represents a fundamental shift in human perspective, from a single-planet species to a Dabbler multi-world civilization. This expansion offers potential solutions to resource limitations, environmental challenges, and existential risks that face humanity on Earth. The study of moon formation and evolution provides insights into the processes that shapes not only our solar system but planetary systems throughout the galaxy. Understanding how satellites form, migrate, and influence their parent planets helps predict the characteristics of exoplanet systems and assess their potential for harboring life. The diverse environments found on different moons expand our conception of habitability and the range of conditions under which life might emerge and survive. From the high-pressure depths of Europa's ocean to the organic-rich surface of Titan, these worlds challenge traditional assumptions about the requirements for life and suggest that biology might be more adaptable than previously thought. The gravitational interactions within complex moon systems provide natural laboratories for studying NBAD dynamics, resonance phenomena, and orbital evolution that have applications in understanding asteroid families, planetary ring systems, and the long-term stability of planetary systems around other stars. The magnetic field studies conducted of various moons contribute to our understanding of dynamo processes, plasma physics, and the interaction between magnetic fields and atmospheres. This knowledge has applications in understanding Earth's magnetic field, predicting space weather effects, and developing magnetic confinement systems for fusion energy. The geological processes observed on different moons, from impact cratering to cryovolcanism to tidal deformation, provide insights into planetary evolution that help scientists understand the history of terrestrial planets and predict the characteristics of rocky exoplanets around other stars. As we conclude our extensive journey through the mysterious moons of the universe, we find ourselves at the threshold of an era when these distant worlds will become not just objects of scientific study, but potential destinations for human exploration and even settlement. The knowledge we have gained about their compositions, environments, and potential for life will guide the development of technologies and strategies needed to extend human presence throughout the solar system. The moons we have encountered represent far more than mere satellites orbiting distant planets. They are complete worlds in their own right, each with unique characteristics, complex histories, and potential futures that could include human presence. From the familiar face of our own moon, which has guided human civilization and will likely serve as our first stepping stone to the cosmos, to the alien environments of Europa and Titan that may harbor life forms unlike anything on Earth, these worlds expand our understanding of the incredible diversity possible in planetary systems. The technological achievements required to explore these distant moons have already transformed life on Earth in countless ways, and future missions will undoubtedly continue this pattern of innovation and discovery. The international cooperation required for these ambitious endeavors demonstrates humanity's capacity to work together toward common goals that transcend national boundaries and political divisions. The potential discovery of life on any of these worlds would rank among the most significant findings in human history, fundamentally altering our understanding of biology, evolution, and our place in the cosmic community. Even if life is not found, the detailed study of the chemical processes occurring on these worlds will provide unprecedented insights into the conditions that allow life to emerge, and the factors that determine whether worlds become biologically active. The environmental lessons learned from studying the diverse climates and atmospheric processes on various moons provide crucial perspective on the factors that make Earth habitable and the care required to maintain the delicate balance of our planetary environment. The extreme conditions found on these alien worlds remind us of how special and precious our own world truly is. The economic, technological, and cultural benefits of moon exploration will continue to accrue for generations, creating new industries, inspiring future scientists and engineers, and expanding human knowledge and capability. The investment in these endeavors pays dividends not only in scientific understanding, but in technological advancement, international cooperation, and cultural enrichment. The long-term vision of human expansion beyond Earth, guided by the knowledge gained through the study of moons throughout the solar system, offers hope for addressing the challenges facing our species and ensuring the long-term survival and prosperity of human civilization. The resources available on these distant worlds, from the water ice that could provide fuel and life support to the rare materials needed for advanced technologies, could support human communities throughout the solar system. The philosophical implications of discovering potentially habitable environments on numerous moons throughout our solar system, and by extension around other stars, challenge us to reconsider fundamental questions about the nature and prevalence of life in the universe. The possibility that life might be common rather than rare, distributed throughout countless hidden oceans and alien environments, suggests that we live in a universe far more biologically rich and diverse than Capri previously imagined. As we look toward the future of moon exploration, we see a progression from robotic reconnaissance to sample return missions to eventual human exploration and potentially permanent settlement. Each step in this progression will build upon the knowledge gained from previous missions and drive the development of new technologies and capabilities that benefit all of humanity. The moons we have explored in our journey tonight will continue to reveal their secrets through future missions and advancing technology. New discoveries will challenge our theories, inspire new questions, and drive further exploration. The cycle of discovery, understanding, and renewed curiosity that characterizes all great scientific endeavors will continue to operate as we delve deeper into the mysteries these worlds contain. In the gentle glow of moonlight that has guided travelers for millennia, in the hidden oceans that may teem with alien life, in the volcanic fires that illuminate the darkness of space, and in the complex orbital dances that create stability and change throughout planetary systems, we find reflections of the fundamental processes that govern the universe and shape the conditions necessary for matter to organize itself into ever more complex and beautiful forms. The mysterious moons of our universe stand as testament to the incredible creativity of natural processes operating over vast scales of space and time. They remind us that we live in a cosmos where water can exist as liquid beneath sheets of ice billions of miles from the nearest star, where organic chemistry can create complex molecules in environments utterly unlike Earth, and where gravitational forces can generate enough energy to power geological processes that reshape entire creation. Worlds. These worlds invite us to continue pushing the boundaries of knowledge and exploration, to maintain our sense of wonder at the incredible diversity of the universe, and to remember that every answer we discover leads to new and even more fascinating questions. The moons that orbit distant planets in the far reaches of our solar system, the potential exomoons that may circle planets around other stars, and the countless variations on the theme of satellite formation and evolution that likely exist throughout the galaxy all await our discovery and understanding. As long as humans retain their fundamental drive to explore and understand the world around them, these mysterious moons will continue to beckon us forward, offering their secrets to those willing to undertake the challenging journey of scientific discovery. In their silent orbits and ancient surfaces, in their hidden oceans and exotic atmospheres, in their complex gravitational relationships and potential for harboring life, we find endless inspiration for the continued exploration of our cosmic neighborhood and the search for our place within the vast and magnificent universe we call home. The rhythmic cycles that govern the movements of these distant worlds create a cosmic symphony that has played for billions of years, a celestial music that speaks to the fundamental harmonies underlying all of nature. The orbital resonances that link Europa, Ganymede, and Io in their gravitational dance around Jupiter create patterns of mathematical beauty that reflect the deep order embedded in the structure of the universe itself. These resonances, where orbital periods form simple ratios like 2:1 or 3:2, demonstrate how gravitational forces naturally organize matter into stable, harmonious key configurations. The same mathematical relationships that govern the movements of moons around planets also appear in the vibrations of musical strings, the oscillations of pendulums, and the quantum mechanical behavior of atoms. This universality of mathematical harmony suggests that the patterns we observe in satellite systems reflect fundamental principles that operate at all scales of the universe, from the subatomic to the cosmic. The seasonal variations observed on moons like Titan, where methane weather systems shift and evolve over decades-long cycles, provide glimpses into the kinds of long-term patterns that may characterize stratus planetary systems throughout the galaxy. These extended seasonal cycles, driven by the orbital mechanics of distant worlds, create environmental changes that unfold over timescales far longer than human lifetimes, reminding us that the universe operates according to rhythms vastly different from those that govern human experience. The geological layers preserved in the ice shells of moons like Europa and Ganymede contain records of environmental changes that span millions or billions of years, creating natural archives that document the evolution of planetary systems over cosmic time. These frozen libraries preserve information about past climate conditions, impact events, and internal processes that shaped these worlds throughout their histories. Future missions that drill through these ice layers would essentially be conducting archaeological excavations of cosmic history. The complex organic chemistry occurring in the thick atmosphere of Titan creates a natural laboratory where scientists can observe the formation of complex carbon compounds under conditions that may have been common throughout the early universe. The organic molecules that rain down onto Titan's surface represent the same kinds of compounds that may have served as the building blocks for life throughout the cosmos, providing insights into the chemical processes that preceded the emergence of biology. The magnetic field interactions that occur around moons like Ganymede create miniature versions of the same processes that generate auroras on Earth and influence space weather throughout planetary systems. These scaled-down versions of large-scale phenomena provide opportunities to study fundamental plasma physics processes under controlled conditions that would be impossible to reproduce in terrestrial laboratories. The impact craters that cover the surfaces of many moons serve as natural chronometers that record the bombardment history of the solar system and provide insights into the violent processes that shaped planetary systems. During their early evolution, by studying the size distributions and ages of craters on different moons, scientists can reconstruct the timeline of major impact events and understand how the flux of impacting objects has changed over billions of years. The subsurface oceans hidden beneath the ice shells of multiple moons represent some of the largest bodies of liquid water in the solar system, potentially containing more water than all of Earth's oceans combined. These hidden seas, maintained by tidal heating and insulated from the harsh conditions of space, could provide stable environments for life to emerge and evolve over geological timescales. The diversity of ice types found on different moons reflects the varied pressure and temperature conditions that exist throughout the outer solar system. From the familiar water ice that forms Earth's glaciers to the exotic high-pressure ice phases that may exist in the deep interiors of large moons. These materials demonstrate how the same basic molecule can take on radically different forms under different environmental conditions. The volcanic processes observed on moons like Io provide insights into the kinds of geological activity that may have been common on terrestrial planets during the early history of the solar system. The sulfur volcanism that creates Io's colorful surface may be similar to processes that operated on the early Earth, when volcanic activity was much more intense and the atmosphere had a very different composition. The cryovolcanic activity observed on moons like Enceladus demonstrates that volcanic processes can operate using materials other than molten rock, expanding our understanding of how planetary interiors can remain active even at extremely low temperatures. These ice volcanoes, which erupt water and other volatiles instead of lava, may be common features on icy bodies throughout the outer solar system and beyond. The gravitational surveys conducted at various moons have revealed internal structures that are far more complex than initially expected, with differentiated layers, subsurface oceans, and possibly even metallic cores that generate magnetic fields. These internal investigations demonstrate that even small, seemingly simple worlds can harbor sophisticated structures that rival those found in much larger planets. The atmospheric escape processes observed at moons like Titan show how planetary atmospheres can evolve over time as gases are lost to space through various mechanisms. Understanding these processes is crucial for predicting the long-term evolution of planetary atmospheres and assessing the habitability of worlds around other stars where similar processes would operate. The ring-moon interactions observed around Saturn demonstrate how gravitational relationships between satellites and ring particles can create complex dynamical structures that persist for millions of years. These interactions provide natural laboratories for studying how material is exchanged between solid bodies and particulate systems, processes that may be important in the formation of planetary nebulae systems around other stars. The capture and evolution of irregular satellites around the giant planets provide insights into the early history of the solar system, when large-scale orbital migrations may have scattered objects throughout the Dactyl outer regions. Understanding these capture processes helps scientists reconstruct the complex gravitational interactions that shaped the final architecture of our planetary system. The search for biosignatures in the atmospheres and surface materials of potentially habitable moons drives the development of increasingly sensitive analytical techniques that have applications far beyond astrobiology. The ability to detect trace amounts of organic compounds, isotopic signatures of biological processes, and other indicators of life benefits, medical diagnostics, environmental monitoring, forensic science. The extreme longevity of some geological processes on moons, where surface features can persist for billions of years due to low erosion rates and minimal atmospheric weathering, provides opportunities to study ancient processes that have been erased from more geologically active worlds. These preserved landscapes serve as windows into the early conditions that existed throughout the solar system. The tidal forces that shape the evolution of moon orbits and drive geological activity also influence the long-term stability of planetary systems, determining which satellites will survive over cosmic timescales and which will eventually be destroyed or ejected. Understanding these tidal evolution processes is crucial for predicting the long-term fate of satellite systems and assessing the stability of potentially habitable moons around exoplanets. The thermal evolution of moons with substantial ice inventories depends on the balance between heat sources like radioactive decay and tidal heating versus heat loss through conduction and radiation. This thermal balance determines whether subsurface oceans can persist over geological time and influences the geological activity that creates surface features and drives chemical evolution. The chemical evolution that occurs in subsurface oceans depends on the interaction between liquid water and rocky cores, processes that can create the kinds of chemical gradients and energy sources that life form bar requires. The hydrothermal systems that may exist at the bottom of these hidden seas could provide the same kinds of environments that supported the earliest life on Earth. The seasonal transport of volatiles on moons like Triton and Pluto demonstrates how thin atmospheres can undergo dramatic changes as different regions are alternately heated and cooled by changing gas. Solar illumination. These processes provide insights into how atmospheric dynamics operate under conditions very different from those found on Earth. The magnetic shielding provided by some moons helps protect their surfaces and atmospheres from the intense radiation environments that exist around giant planets. This shielding may be crucial for maintaining stable surface conditions and preventing atmospheric loss, factors that could determine the habitability of moon systems around gas giant exoplanets. The complex orbital relationships that exist in some moon systems create long-term cycles of gravitational influence that can drive episodic geological activity, atmospheric changes, and surface evolution. These cycles, which may extend over millions of years, demonstrate how satellite systems can undergo periodic variations that dramatically alter environmental conditions. The potential for panspermia, the transfer of life between worlds, may be enhanced in systems with multiple moons where material ejected from one satellite by impacts could eventually reach other satellites. This possibility suggests that if life emerges on one moon in a system, it might eventually spread to other suitable environments within the same planetary system. The study of moon formation through computer simulations has revealed the incredible complexity of the processes that create satellite systems, involving not only gravitational dynamics but also thermodynamics, fluid mechanics, and materials science. These simulations help scientists understand how the initial conditions in planetary systems influence the final characteristics of moon systems. The spectroscopic analysis of moon surfaces from Earth-based telescopes continues to reveal new details about composition, mineralogy, and surface processes that complement the findings from spacecraft missions. These ground-based observations demonstrate how remote sensing techniques can extract detailed information about worlds billions of kilometers away. The development of artificial intelligence systems for autonomous spacecraft operations at distant moons has applications for robotic systems operating in extreme environments on Earth, from deep ocean exploration to polar research. The ability to make complex decisions autonomously during long communication delays benefits any situation where remote control is impractical. The psychological and sociological studies of human crews on simulated missions to distant moons provide insights into group dynamics, leadership, and mental health that have applications for any situation involving small teams working in isolation under stressful conditions. These studies contribute to better understanding of human factors in extreme environments. The resource utilization techniques being developed for potential moon bases, including water extraction from ice deposits, oxygen production from rock, and construction using local materials, have terrestrial applications for sustainable development and resource conservation. Learning to live sustainably on resource-limited moons informs approaches to sustainable living on Earth. The closed-loop life support systems required for long-duration missions to distant moons must achieve levels of recycling efficiency that exceed anything currently used on Earth. The development of these systems drives advances in environmental control technology that benefit terrestrial applications from submarines to space stations. As we reach the final moments of our cosmic journey through the realm of mysterious moons, we find ourselves profoundly changed by the experience of contemplating these alien worlds and their hidden secrets. The universe revealed through our exploration is far richer, more complex, and more potentially life-bearing than we could have imagined when we first began to peer beyond our earthly bounds. Each moon we have encountered has expanded our conception of what is possible when matter and energy interact under the influence of gravity and time, creating worlds of stunning beauty and endless fascination. The technological achievements that have enabled us to study these distant realms represent some of humanity's greatest accomplishments, demonstrating our species' remarkable ability to extend our senses and presence far beyond the confines of our home planet. From the robotic explorers that have visited Jupiter's moons to the telescopes that peer into the depths of space, searching for exomoons around distant stars, we have created extensions of human curiosity and ingenuity that allow us to explore realms once accessible only to imagination. The knowledge gained from studying these mysterious moons has applications that extend far beyond pure scientific research, influencing technology development, environmental science, astrobiology, and our fundamental understanding of planetary processes. This knowledge helps us better appreciate the uniqueness and fragility of our own world, while opening our eyes to the incredible diversity of environments that exist throughout the cosmos. The future holds the promise of even more remarkable discoveries as our exploration of these enigmatic worlds continues with increasingly sophisticated missions and technologies. The possibility of finding life in the subsurface oceans of Europa or Enceladus, of understanding the complex organic chemistry occurring on Titan, or of discovering entirely new types of geological processes on previously unexplored moons, keeps the flame of scientific curiosity burning brightly. In the quiet majesty of these distant worlds, in their ancient surfaces that have witnessed billions of years of cosmic history, in their hidden oceans that may harbor life unlike anything on Earth, and in their continuing evolution under forces we are only beginning to understand, we find profound lessons about the nature of our universe, our place within it. The mysterious moons that have guided our journey tonight will continue to inspire wonder, drive discovery, and expand human knowledge for generations to come, ensuring that the sense of awe and curiosity that first drew us to look up at the night sky will continue to propel us outward into the cosmic vastness, seeking always to understand the magnificent complexity, beauty of the universe we call home.